Reality is a word you use every day. You use it to separate what's true from what isn't, what exists from what doesn't, what happened from what you imagined. It feels like the most solid concept we have. The ground beneath your feet is real. The screen in front of you is real. Your body, your breath, the room around you, all real. But when you begin to examine what that word actually means, something unexpected happens. The certainty starts to dissolve. Not because reality itself is uncertain, but because what we call reality turns out to be far stranger than the simple, solid thing we assume it to be. Physics has spent the last century discovering that the universe doesn't work the way our senses tell us it does. Matter isn't solid. Time isn't universal. Observation isn't passive. The very act of looking at something changes it. The present moment you're experiencing right now might not be more real than the past or future. And at the smallest scales, things don't even exist in definite states until something interacts with them. This isn't philosophy. These are measurements, experiments, repeatable observations that have forced us to reconsider what we mean when we say something is real. You've built your entire understanding of existence on assumptions that feel obvious, that objects have definite positions, that time flows forward, that the world exists independently of whether anyone is looking at it. These assumptions work perfectly well for living your life, but they are not descriptions of how the universe actually operates. What follows is not an attempt to prove reality is an illusion, or that nothing matters. It's the opposite. It's an exploration of what reality actually is, beneath the convenient approximations our brains construct. And understanding that doesn't make the universe less real. It makes it deeper, stranger, more intricate than any human mind was built to naturally comprehend. This is what happens when you stop taking reality for granted and start asking what the word actually means. You're sitting somewhere right now, perhaps in a chair, perhaps on a bed or a couch. Whatever surface is beneath you feels solid. It supports your weight. It doesn't allow your body to pass through it. If you press your hand against a table or a wall, it resists. This resistance feels like the most fundamental proof of reality. The world pushes back. It has substance. It is there. This experience is so consistent, so reliable, that it forms the foundation of how you understand existence itself. Solid things are real. They occupy space. They persist. They don't vanish or change unless something acts on them. This is what matter means to you. This is what physical reality feels like. But that feeling is not an accurate description of what is actually happening. The chair you're sitting on is made of atoms. You learned this in school, probably without thinking much about it. Atoms are small. They're the building blocks of matter. They stick together to form molecules, and molecules form objects, and objects form the world. This explanation feels complete enough. It explains why things are solid without requiring you to think about it further. But atoms themselves are almost entirely empty space. Not metaphorically, not approximately, almost entirely empty. The nucleus of an atom, the dense cluster of protons and neutrons at its center, is incredibly small compared to the overall size of the atom. If you scaled an atom up so that its nucleus was the size of a marble, the electrons orbiting it would be more than half a mile away. Everything in between is empty. No particles, no stuff, just fields and forces and space. The chair you're sitting on is more than 99.9% empty space. So is your body. So is the floor beneath you. Every solid object you have ever touched is a sparse cloud of particles held together by forces with vast emptiness between them. And yet you don't fall through the chair. Your hand doesn't pass through the table. The world behaves as if it is solid, even though it is not. What you interpret as solidity is not matter touching matter. It is a repulsive electromagnetic force. Electrons in the atoms of your body are negatively charged. Electrons in the atoms of the chair are also negatively charged, like charges repel. When you sit down, the electrons in your body and the electrons in the chair push against each other, with enough force to prevent them from occupying the same space. You never actually touch the chair. You hover above it, suspended by an electromagnetic field, separated by a distance so small that your nervous system interprets it as contact. Every surface you have ever felt, every object you have ever held, every handshake and hug and footstep, none of them involved actual touch. You have never touched anything in your life. You have only felt the repulsion of electric fields preventing atoms from getting too close. This is not an abstraction. This is what is happening right now as you sit or stand or lie down. The sensation of solidity is your brain's interpretation of forces, not of matter, and those forces are not generated by particles colliding. They are generated by fields interacting across empty space. Think about what this means for a moment. The floor beneath your feet is not a continuous surface. It is a lattice of atomic nuclei, each one surrounded by a cloud of electrons, with vast distances between them at the atomic scale. The spaces between these nuclei are not filled with anything physical. There is no medium there, no substance, just the mathematical structure of quantum fields that govern how particles behave. When you walk across a room, your feet do not make contact with a solid surface. The electrons at the surface of your skin approach the electrons at the surface of the floor, and electromagnetic repulsion prevents them from getting closer. This repulsion is strong enough to support your entire body weight. It is strong enough to feel like contact, but it is not contact. It is a force transmitted across a gap that your senses are not equipped to detect. At this scale, the distinction between something being there and something not being there starts to blur. A particle is not a tiny sphere sitting in a specific location. It is a ripple in a field, a concentration of energy that behaves as if it has a position only when something interacts with it. Between interactions, it exists as a probability distribution, a cloud of potential locations where it might be found if you were to look. The table in front of you is not a collection of solid objects. It is a pattern of quantum fields in a configuration stable enough to persist over time. The forces holding it together are not physical bonds in the way you imagine bonds. They are excitations in electromagnetic and quantum chromodynamic fields, manifesting as what we call particles, which then interact according to rules that prevent them from interpassing. You can push against a wall and it will not give way, but the wall is not resisting because it is full of substance. It is resisting because the quantum fields that compose it are in a low energy state that requires an enormous amount of energy to disrupt. Solidity is not a property of matter, it is a property of energy configurations in fields. This is where human intuition begins to fail, because the world still looks solid. It still feels solid. Your experience has not changed, and yet the explanation for why it feels that way has become completely alien to the way you naturally think about objects in space. Consider the history of how we came to understand this. For most of human existence, matter was simply matter. It was the stuff things were made of. It had weight, texture, colour, temperature. It was real in the most obvious sense. Philosophers debated whether matter was infinitely divisible or made of fundamental particles. But these debates were theoretical. No one could actually see atoms or measure them. It wasn't until the early 20th century that experiments began to reveal the structure of atoms in detail. Ernest Rutherford's gold foil experiment in 1911 showed that atoms were mostly empty space with a dense nucleus. This was shocking at the time. Scientists had assumed atoms were more like tiny spheres of uniform density. The discovery that they were almost entirely void was counterintuitive and difficult to accept, but the evidence was undeniable. When Rutherford's team fired alpha particles at a thin sheet of gold foil, most of them passed straight through as if nothing was there. Only a tiny fraction bounced back, indicating they had hit something very small and very dense. The only explanation was that the gold atoms were mostly empty, with all their mass concentrated in a nucleus far smaller than the atom itself. This discovery changed everything. It meant that the solid world around us was an illusion in a very literal sense. Not an illusion in that it doesn't exist, but an illusion in that our perception of it as solid, continuous and substantial does not match its actual structure. You were taught that matter is made of atoms, and atoms are made of smaller particles, and that was enough. But those particles are not little balls of stuff. They are quantum excitations. The universe is not made of things. It is made of fields and energy, arranged in patterns that our brains interpret as objects. Even the forces that create the sensation of solidity are not what you think they are. The electromagnetic force is not a push or a pull in the mechanical sense. It is an exchange of virtual photons between charged particles. These photons are not real in the sense that you could detect them individually. They exist only as mathematical terms in the equations that describe how particles interact. And yet, they are responsible for every sensation of touch you have ever experienced. The strong nuclear force, which holds protons and neutrons together in the nucleus, is even stranger. It operates through the exchange of particles called gluons, which interact with quarks, the particles that make up protons and neutrons. Quarks are never found in isolation. They're always bound together by the strong force, and the energy required to separate them is so enormous that attempting to do so simply creates new quarks instead. This is called quark confinement, and it means that the particles we think of as fundamental are themselves made of components that cannot exist independently. The world you experience as solid is held together by forces you cannot see, operating on particles you cannot touch, in a structure that is mostly empty space. And this is only the beginning. Because if matter is mostly empty space and solidity is an illusion created by forces, then what are you actually sensing when you look at the world? What does it mean to see something? What is vision actually detecting? The answer is not as straightforward as it seems. You open your eyes and you see the world. This feels immediate, direct, unmediated. Light enters your eyes and you perceive shapes, colours, distances, textures. Vision seems like the most reliable way to know what is real. You see the chair, therefore the chair exists. You see the walls of the room, therefore the room is there. Seeing is believing. But vision is not direct observation of reality. It is interpretation of a narrow slice of information that happens to interact with the cells in your retina. And that slice is far smaller than you realise. Light is electromagnetic radiation. It travels as waves of oscillating electric and magnetic fields, propagating through space at a fixed speed. The electromagnetic spectrum is vast. It includes radio waves with wavelengths longer than a building, microwaves that heat your food, infrared radiation that you feel as warmth, visible light that you see, ultraviolet radiation that burns your skin, X-rays that pass through your body, and gamma rays energetic enough to ionize atoms. All of these are the same phenomenon, just at different wavelengths and frequencies. You can see only a tiny fraction of this spectrum. The visible range spans wavelengths from about 400 nanometers to 700 nanometers. A nanometer is 1/1000th of a meter. The difference between the longest wavelength you can see and the shortest is less than a factor of 2. This is an extraordinarily narrow band. If the entire electromagnetic spectrum were represented as a piano keyboard stretching from one end of the universe to the other, the part you can see would be narrower than a single key. Everything else is invisible to you, not because it isn't there, but because your eyes did not evolve to detect it. The photoreceptor cells in your retina, rods and cones, respond only to photons within this narrow range of energies. Photons with slightly longer wavelengths pass through your retina without triggering any response. Photons with slightly shorter wavelengths do the same. Your experience of vision is determined not by what exists, but by what your biology can detect. This is not a minor limitation. It means that most of what is happening around you electromagnetically is completely invisible. Right now, radio waves are passing through your body. They carry information, television broadcasts, Wi-Fi signals, cell phone data, but you cannot perceive them. Infrared radiation is being emitted by every warm object in the room, including your own body, but you cannot see it. Ultraviolet light from the sun is entering through the window if it is daytime, but you have no direct awareness of it. The world you see is not the world as it is. It is a reconstruction based on the limited data your eyes can gather. Your brain receives electrical signals from your retina and interprets them as colours, edges, motion, depth. But colour does not exist in the external world. There is no red or blue or green in the light itself. There are only photons of different wavelengths. Your brain assigns colours to those wavelengths as a way of organising the information. Red is simply your brain's label for light with a wavelength around 650 nanometers. The experience of redness, the quale, the subjective sensation, exists only in your mind. Consider what this means. The colours you see are not properties of objects. They are properties of the interaction between light, objects, and your visual system. A red apple is not red in any absolute sense. It absorbs most wavelengths of visible light and reflects wavelengths around 650 nanometers. Those reflected photons enter your eye, strike your retina, and trigger a cascade of neural signals that your brain interprets as the colour red. If you were a different species with different photoreceptors, the apple would look entirely different. If you had no eyes at all, the concept of colour would be meaningless. Many animals see a different range of the electromagnetic spectrum than you do. Bees can see ultraviolet light. To a bee, flowers have patterns and colours that are completely invisible to you. The flower looks one way to you and an entirely different way to the bee, and neither perception is more correct than the other. They are simply different interpretations of the same electromagnetic information. Some snakes can detect infrared radiation, allowing them to see heat. They perceive warm-blooded animals as glowing shapes in the darkness, a form of vision that has no equivalent in human experience. The mantis shrimp has 16 types of photoreceptor cells, compared to the 3 types in human eyes. This does not necessarily mean they see more colours in the way you understand colour, but it does mean their visual experience is fundamentally different from yours. They can detect polarised light, which is invisible to you. They can distinguish between different types of circular polarisation. Their reality, constructed from vision, is richer in dimensions that you cannot even imagine. This raises an uncomfortable question. If different species see the world in completely different ways based on their sensory biology, which version is real? The answer is that none of them are complete. Each species detects a subset of the available information and constructs a model of reality based on that subset. Your version of reality is human reality. It is real in the sense that it corresponds to actual physical processes, but it is not complete. It is not the territory. It is a map, and the map is drawn according to the limitations of your senses. Even within the narrow band of light you can see, your perception is not straightforward. Your eyes do not record the world like a camera. They move constantly in rapid, jerky motions called saccades, 3 to 4 times per second. During a saccade, your vision is suppressed. You're effectively blind for a fraction of a second. Your brain fills in the missing information based on memory and prediction. You do not notice this because the stitching together of these fragments happens unconsciously. Your retina also has a blind spot where the optic nerve exits the eye. There are no photoreceptors there. You have a hole in your vision, but you never see it because your brain fills it in with surrounding visual information. You can demonstrate this to yourself with a simple experiment, but in ordinary experience you remain unaware of it. Your brain does not show you what your eyes see. It shows you a constructed, edited version designed to be useful. The center of your vision, the fovea, has high resolution. The periphery does not. You can only see fine detail in a small area at the center of your visual field. Everything else is blurry, low resolution, filled in by your brain based on context and expectation. You move your eyes constantly to sample different parts of the scene, and your brain integrates this information into the experience of seeing a complete detailed image. But that complete image does not exist in your eyes. It exists only in your mind. And even this constructed image is limited to the surface of objects. You see the outside of things, the boundary where light reflects or scatters. You do not see inside them. You do not see the atomic structure or the spaces between atoms. You see only the interaction between light and matter at a macroscopic scale. When light strikes an object, several things can happen. It can be absorbed, converted into heat. It can be reflected, bouncing off the surface. It can be transmitted, passing through if the material is transparent. It can be scattered, deflecting in random directions. The combination of these interactions determines what you see. A transparent object like glass allows most light to pass through, which is why you can see through it. An opaque object like wood absorbs or reflects most light, which is why you cannot. But transparency and opacity are not fundamental properties. They are just descriptions of how materials interact with photons in the visible range. Some materials that are opaque to visible light are transparent to other wavelengths. Your body is opaque to visible light but partially transparent to X-rays, which is why X-ray imaging works. Walls that block visible light do not block radio waves, which is why you can use a cell phone indoors. The concept of an object being solid or opaque is wavelength dependent. It is not an intrinsic property of the object itself. This means that what you see is not what an object is. It is how an object interacts with a narrow range of electromagnetic radiation. The chair you're sitting on looks solid and brown or black or blue, but those are not descriptions of the chair's fundamental nature. They are descriptions of how the chair's surface atoms interact with photons in the visible spectrum. To a radio wave, the chair barely exists. To an X-ray, it is partially transparent. To a neutrino, it is not there at all. The neutrino passes through the chair, through the earth, through everything, as if it were empty space. So what is the chair really? What is its objective nature independent of observation? Physics does not provide a simple answer to this question. The chair is a configuration of quantum fields. It interacts with different types of radiation in different ways. It has properties like mass, charge, and temperature. But none of these properties constitute a complete picture of what the chair is in itself. They're all relational. They describe how the chair interacts with other things. Your vision gives you information about one specific type of interaction, the scattering and absorption of visible light. This information is useful. It allows you to navigate the world, recognize objects, avoid obstacles. But it is not a direct perception of reality. It is a highly processed interpretation of a narrow subset of the available data. And that subset was selected not because it is more real, but because it was useful to your ancestors. Evolution shaped your senses to detect the information that improved survival and reproduction. It did not shape them to perceive objective reality. The world you see is a user interface. It is a simplified, schematic representation designed to help you interact with your environment. It hides complexity. It filters out information that is not immediately relevant. It presents you with colours and shapes and boundaries that make intuitive sense, even though those colours and shapes are constructions that do not exist outside your mind. And if vision, the sense you trust most, is this limited, this indirect, this constructed, then what does that imply about your other senses? What does it imply about your overall perception of reality? The answer is that everything you experience is mediated, filtered, interpreted. You do not have direct access to the external world. You have access only to your brain's model of it. And that model is built from incomplete data, processed through biological systems that evolve for survival, not for truth. You experience time as a flow. The past is behind you, fixed and unchangeable. The future is ahead, uncertain and not yet real. The present is now, the only moment that exists. This feels obvious, undeniable. Time moves forward. Events happen in sequence. Cause precedes effect. You remember yesterday but not tomorrow. You age but you do not get younger. Time is the most fundamental structure of your experience. But according to physics, this structure is not built into the universe. The flow of time, the distinction between past and future, the special status of the present moment, none of these appear in the fundamental equations that describe how reality works. Time does not flow in physics, it simply is. And the direction we call forward is not a property of time itself. It is a property of entropy, of information, of memory and causation. It is emergent, not fundamental. The equations of physics are time-symmetric. If you take any physical process described by these equations and reverse the direction of time, the equations still work. A ball thrown into the air follows a parabolic path. If you played a video of this in reverse, the ball would follow the same path backward, and nothing in the equations would indicate that one direction is correct and the other is not. Particles colliding and scattering can be run forward or backward in time, and the mathematics remains consistent. At the level of fundamental physics, there is no preferred direction to time. This seems impossible. You can break an egg, but you cannot unbreak it. You can watch a cup fall and shatter, but you never see the shards spontaneously leap back together. The universe clearly has a direction. Things decay. They do not spontaneously repair themselves. Heat spreads out. It does not spontaneously concentrate. You age. You do not grow younger. The past is different from the future in every meaningful way. The resolution to this paradox lies in the second law of thermodynamics. Entropy, the measure of disorder or the number of possible microstates consistent with a macroscopic state, tends to increase over time in a closed system. This is not because the fundamental laws prefer increasing entropy. It is because there are vastly more high-entropy states than low-entropy states. If you start in a low-entropy configuration, random processes will almost certainly move you toward higher entropy, simply because there are more ways to be disordered than to be ordered. When you break an egg, you're moving from a low-entropy state, an intact, organized structure, to a high-entropy state, a scattered, disordered mess. The reverse process is not forbidden by physics. The molecules of the broken egg could, in principle, spontaneously rearrange themselves into an intact egg. but the number of configurations that correspond to a broken egg is astronomically larger than the number that correspond to an intact one. The probability of the reverse process happening by chance is so small that you would have to wait longer than the age of the universe to see it occur. This is why time has a direction. Not because time itself flows, but because the universe started in a low entropy state, and entropy has been increasing ever since. The Big Bang was an extraordinarily low entropy event. All the matter and energy in the universe was concentrated in a small, hot, dense state. Since then, the universe has been expanding and cooling, and entropy has been increasing. The arrow of time is the arrow of entropy. It points from low entropy to high entropy, from order to disorder, from the Big Bang to the heat death of the universe. But this raises a deeper question. Why did the universe start in a low entropy state? If high entropy states are so much more probable, why didn't the universe begin in a state of maximum entropy? The answer is that we do not know. This is one of the most profound unsolved problems in cosmology. The low entropy initial condition of the universe is not explained by any current theory. It is simply a boundary condition we must accept, and it is this unexplained boundary condition that gives time its direction. Your perception of time is built on this thermodynamic arrow. You remember the past because memory is a physical record, and records can only form in the direction of increasing entropy. When you form a memory, you are creating a low entropy structure in your brain, a specific pattern of neural connections that encodes information about an event. This process increases the total entropy of the universe because forming the memory generates heat and disorder elsewhere. But locally, temporarily, your brain reduces its own entropy by organizing information. This is only possible because the universe as a whole is moving toward higher entropy. You do not remember the future because memory formation is an irreversible process tied to the thermodynamic arrow. If entropy were decreasing, you would remember the future and not the past. But in a universe where entropy is increasing, causation runs from past to future, and memory follows causation. This means that your sense of time is not a perception of time itself. It is a perception of entropy gradients and causal structures. You feel time moving forward because you are embedded in a physical system where entropy is increasing and where causes leave traces in the form of records and memories. If the universe were in a state of maximum entropy, a state of total thermodynamic equilibrium, there would be no arrow of time, no change, no memory, no distinction between past and future. Time would still exist as a dimension, but it would have no direction. And this is where physics becomes unsettling. Because if the fundamental equations are time-symmetric, then the distinction between past and future is not written into the structure of space-time. It is a feature of the particular configuration the universe happens to be in. And that configuration is not necessary, it is contingent. The universe could have started in a high-entropy state, or it could evolve toward a state where entropy decreases. In such a universe, the arrow of time would point the other way, or it would not exist at all. Even the concept of the present moment is problematic. In your experience, the present is special. It is the only time that is real. The past is gone. The future has not yet arrived. But in Einstein's theory of relativity, there is no universal present. Simultaneity, the question of which events happen at the same time, depends on your state of motion. Two observers moving relative to each other will disagree about whether two distant events occur simultaneously. One observer might see event A happen before event B, while another observer sees event B happen before event A. Both observations are correct within their own reference frames. This means that the present moment is not a universal feature of the universe. It is relative, observer-dependent. What you call now is not the same as what someone else moving relative to you calls now. And if the present is not universal, then the idea that only the present moment exists becomes incoherent. If different observers have different present moments, then which one is real? The only consistent answer is that all moments are equally real. The past and the future exist just as much as the present. They are simply different locations in space-time. This view is called eternalism or the block universe. In this picture, space-time is a four-dimensional structure in which all events, past, present and future, exist simultaneously. Time is just another dimension, like space. You move through time the way you move through space. but you do not experience it that way because your consciousness is extended through time in a particular direction. You remember the past and not the future because memory is a thermodynamic process tied to the arrow of entropy. But the future exists just as much as the past. It is simply elsewhere in space-time. This is difficult to accept. It feels wrong. Your experience tells you that the present is real and the future is not yet determined. You make choices. You feel that you are shaping the future. But in the block universe, the future already exists. Your choices are already part of the structure. The sensation of free will, of creating the future through your actions, is a psychological phenomenon that occurs within the block. It is real as an experience, but it does not mean that the future is open or undetermined. It means that your experience of making choices is part of the causal structure of space-time. This does not make your choices meaningless. It does not imply fatalism. Your decisions still matter. They still have consequences. Causes still precede effects. But the idea that the future does not yet exist, that it is brought into being by the passage of time, is not supported by relativity. Time does not pass in the sense of creating new moments. All moments exist. What changes is your position in space-time, your location along the time dimension. Philosophers have debated these implications for decades. Some argue that relativity requires eternalism. Others claim that presentism, the view that only the present exists, can be reconciled with relativity if you accept that simultaneity is conventional or that there is a preferred reference frame. But the mainstream interpretation among physicists is that the block universe is the most natural picture consistent with the mathematics of relativity. And if the block universe is correct, then the passage of time is an illusion, not in the sense that time does not exist, but in the sense that the feeling of time flowing, of the present moment moving forward, is a feature of consciousness, not a feature of the universe. The universe does not flow, it simply is. All of space-time exists as a static, eternal structure. What you call the present moment is just your current location in that structure. What you call the past is events at earlier time coordinates. What you call the future is events at later time coordinates. But all of these events exist simultaneously in the four-dimensional block. This means that right now, in some sense, every moment of your life exists. Your birth exists. Your childhood exists. This moment exists. Your death exists. They are all equally real, located at different points along your world line, the path you trace through space-time. You experience these moments sequentially because your consciousness is structured to move through time in one direction. But that directionality is not a property of time itself. It is a property of entropy, of causation, of memory. It is a property of you, not of the universe. You cannot step outside of time to see the block universe as a whole. Your perceptions and thoughts occur at specific moments, and you cannot perceive moments other than your current one. But this limitation does not mean those other moments are unreal. It means your access to reality is constrained by your position in space-time and by the structure of your consciousness. The arrow of time, the flow of time, the specialness of the present, these are not features of reality. They are features of your experience of reality, and that experience is shaped by thermodynamics, by entropy, by the fact that the universe began in a low entropy state and has been evolving toward higher entropy ever since. If the universe had different initial conditions, your experience of time could be completely different, or it might not exist at all. You assume that objects have definite properties whether you're looking at them or not. The cup on the table has a position. It is either on the left side or the right side. The coin in your pocket is either heads up or tails up. A particle moving through space has a location and a velocity. These properties exist independently of your observation. They are real. They are there. This assumption feels so obvious that it is difficult to imagine it could be wrong. But quantum mechanics tells us that this assumption is incorrect. Particles do not have definite properties until they are measured. Before measurement, they exist in a superposition, a combination of all possible states simultaneously. A particle does not have a position. It has a probability distribution of positions. It is not in one place or another. It is, in some sense, in multiple places at once. And this is not because we lack information about where it is. It is because the particle genuinely does not have a definite position until something interacts with it. This is not philosophy. This is measurement. The double-slit experiment demonstrates this with unsettling clarity. You fire a single electron at a barrier with two slits. You might expect the electron to go through one slit or the other, like a marble would. And if you detect which slit it goes through, that is exactly what happens. It goes through one slit, and it arrives at a detector on the other side in a pattern consistent with a particle travelling through a single opening. But if you do not detect which slit the electron goes through, something strange happens. The electron produces an interference pattern on the detector screen, alternating bands of high and low probability, exactly like the pattern you would see if you sent waves through both slits simultaneously. The electron behaves as if it went through both slits at the same time. It interferes with itself. And this is true even when you send the electrons one at a time, with hours between each one. Each individual electron creates a single dot on the screen, but over time those dots build up into an interference pattern. The electron is not just a particle, it is a wave, or more accurately, it is neither a particle nor a wave. It is a quantum object that exhibits properties of both depending on how you measure it. The mathematics that describes this behavior is the wave function. The wave function is a mathematical object that encodes all the information about a quantum system. It evolves smoothly and deterministically according to the Schrödinger equation. But the wave function does not give you the position of a particle. It gives you the probability of finding the particle at a particular position if you measure it. Before measurement, the particle does not have a position. It has a wave function spread out over space. The wave function is the particle, in the sense that there is nothing else. There is no hidden particle with a definite position that the wave function merely describes. The wave function is the complete description of the system. This is profoundly counterintuitive. It means that reality at the quantum level is not made of things with definite properties. It is made of potentialities, possibilities. The particle is not here or there. It is potentially here and potentially there, and both potentialities are real in some sense until a measurement collapses the wave function into one outcome or the other. And this is not limited to position. Momentum, spin, energy, all of these properties exist in superposition until measured. A particle does not have a definite spin before you measure it. It is in a superposition of spin up and spin down. When you measure it, you get one result or the other, but before the measurement, both possibilities coexist. The act of measurement does not reveal a pre-existing value. It creates the value by forcing the system into a definite state. This is where quantum mechanics diverges from any intuitive model of reality. In classical physics, measurement is passive. You measure the position of a ball, and the ball was already in that position before you looked. The measurement reveals information but does not change the system in any fundamental way. In quantum mechanics, measurement is active. It changes the system. It collapses the wave function. It transforms a superposition of possibilities into a single actuality. And the disturbing part is that we do not fully understand how or why this happens. The Schrödinger equation describes how the wave function evolves over time. It is deterministic. Given the wave function at one moment, you can calculate the wave function at any future moment. But when a measurement occurs, the wave function does not evolve according to the Schrödinger equation. It collapses. It jumps discontinuously from a superposition to a definite state. This collapse is not described by the Schrödinger equation. It is an additional postulate added to the theory to match experimental results. But there is no deeper explanation for why or how it happens. This is called the measurement problem, and it is one of the most profound unsolved issues in physics. What counts as a measurement? Does it require a conscious observer? Does it happen when the quantum system interacts with a large classical system? Does the collapse actually happen, or is it just an illusion created by the way we perceive quantum systems? Different interpretations of quantum mechanics give different answers to these questions, and no consensus has been reached. The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg in the early 20th century, takes the pragmatic view that the wave function collapse is real, but that we should not ask what happens before measurement. The wave function is not a description of reality itself, but a tool for predicting measurement outcomes. Asking what the particle is doing when no one is looking is meaningless. The only reality is what we can measure. This interpretation avoids the philosophical questions by refusing to engage with them. It treats quantum mechanics as a set of rules for calculating probabilities, not as a description of an underlying reality. And for practical purposes, this works. Physicists use quantum mechanics to make extraordinarily accurate predictions. The theory has been tested in countless experiments, and it has never been wrong. But it does not tell us what is actually happening. It tells us what we will observe if we perform a measurement. Other interpretations try to provide a deeper picture. The many-worlds interpretation, proposed by Hugh Everett in 1957, eliminates wave function collapse entirely. It says that all possible outcomes of a measurement actually occur, but in different branches of reality. When you measure a particle's spin, the universe splits into two branches, one where you observe spin up and one where you observe spin down. Both outcomes are real. Both versions of you exist. You simply cannot communicate across branches, so each version of you experiences only one outcome. This interpretation solves the measurement problem by denying that collapse happens. The wave function never collapses. It continues to evolve deterministically according to the Schrödinger equation, and what we call collapse is just the branching of the universe into multiple non-interacting realities. But this comes at a significant cost. It requires accepting that an unimaginably vast number of parallel universes exist, each containing slightly different versions of you and everything else. Most physicists find this ontologically extravagant, though the mathematics is clean and internally consistent. Pilot wave theory, or de Broglie bomb theory, takes a different approach. It says that particles do have definite positions at all times, but they are guided by a pilot wave that evolves according to the Schrödinger equation. The wave function is real, and so is the particle, and the particle's motion is determined by the wave function. This restores determinism and eliminates the measurement problem, but it requires accepting non-locality. The pilot wave can instantaneously affect particles at arbitrary distances, violating the intuition that influences should propagate at finite speeds. All of these interpretations reproduce the same experimental predictions. They agree on what you will observe in any given experiment. They differ only in what they say is happening when no one is observing. And because they make the same predictions, there is no experiment that can distinguish between them. The choice of interpretation is a matter of philosophical preference, not empirical evidence. What this means is that quantum mechanics works. It predicts the outcomes of experiments with extraordinary precision, but we do not agree on what it tells us about reality. We do not know whether particles have definite positions when unobserved. We do not know whether the wave function is real or just a calculational tool. We do not know whether measurements cause collapse or branching or neither. We have a mathematical framework that describes the behavior of quantum systems, but we do not have a consensus on what that framework means, and this is not a minor gap in understanding. It is a fundamental uncertainty about the nature of reality itself. At the deepest level we have been able to probe, the universe does not behave the way our intuition suggests it should. Objects do not have definite properties independent of observation. The act of measurement affects the system in ways that cannot be avoided or compensated for. And the boundary between the quantum world and the classical world, the world of everyday objects that seem to have definite properties, is not clearly defined. Large objects like chairs and tables and people appear to behave classically. They do not seem to be in superpositions. You do not see a chair in two places at once. But according to quantum mechanics, the chair is a collection of particles, and each particle is governed by quantum rules. So why does the chair not exhibit quantum behavior? The answer is decoherence. When a quantum system interacts with its environment, with air molecules, photons, thermal radiation, the superposition rapidly becomes entangled with the environment in a way that makes the different branches of the superposition effectively independent. They no longer interfere with each other. From the perspective of an observer within one branch, the superposition appears to have collapsed into a definite state. Decoherence explains why macroscopic objects appear classical, even though they are made of quantum particles. It does not solve the measurement problem, but it explains why we do not see quantum effects in everyday life. The environment acts as a constant measurement apparatus, collapsing or branching or decohering the wave function so rapidly that superpositions of macroscopic objects cannot persist. For a particle in isolation, superpositions can last indefinitely. For a particle in a warm, noisy environment, decoherence happens almost instantaneously. This means that the classical world you experience is an approximation. It is an emergent phenomenon that arises when quantum systems interact with their environments in ways that destroy coherence. The deterministic, definite, observable universe of everyday life is not fundamental. It is a coarse-grained description that emerges from quantum mechanics under specific conditions, and those conditions, isolation from the environment, suppression of decoherence, are extremely difficult to maintain. This is why quantum computers are so hard to build. They require keeping quantum systems isolated from their environment long enough to perform calculations, and any interaction with the environment causes errors. The world you perceive as solid, definite, and real is a higher level description that emerges from a deeper level where nothing is definite and everything is probabilistic. And this is not a failure of knowledge. It is not that the particles have definite properties, and we simply do not know what they are. The particles genuinely do not have definite properties. Reality at the quantum level is fundamentally different from reality at the macroscopic level, and the transition between these levels is not fully understood. When you measure a quantum system, something happens. The wave function, which was spread out over many possible states, suddenly becomes concentrated in one. The particle, which had no definite position, now has one. The electron that was in a superposition of spin up and spin down is now definitely one or the other. This transition is called wave function collapse, and it is the moment when quantum possibilities become classical certainties. But what triggers this collapse? What counts as a measurement? And what is actually happening during the collapse? These questions have no agreed upon answers. The mathematics of quantum mechanics describes the collapse as an instantaneous, discontinuous jump from superposition to a definite state. But it does not explain why this jump occurs or what physical process underlies it. The collapse is simply postulated. It is added to the theory because without it, the theory does not match what we observe. In everyday experience, measurement feels straightforward. You look at a thermometer and it shows a temperature. You weigh an object and the scale shows a mass. The measurement reveals a property that the object already had. But in quantum mechanics, this picture breaks down. The system does not have a definite value before measurement. The measurement does not reveal a pre-existing property, it creates the property. Or at the very least, it selects one possibility from many and makes it real in a way that the others are not. This is not a matter of disturbing the system. You might think that measurement works like this. The particle has a definite position, but when you try to measure it, you have to bounce a photon off it or interact with it in some way, and that interaction disturbs the particle and changes its position. This is how measurement works in classical physics. You cannot measure something without touching it in some way, and touching it might change it. But in quantum mechanics, the issue is deeper. The particle does not have a definite position before the measurement, so there is nothing to disturb. The interaction does not change the position. It causes the position to become definite for the first time. Heisenberg's uncertainty principle captures part of this. It states that you cannot simultaneously know both the position and momentum of a particle with arbitrary precision. The more accurately you measure the position, the less accurately you can know the momentum and vice versa. This is not a limitation of your measuring instruments. It is a fundamental property of quantum systems. Position and momentum are complementary variables. A particle cannot have a definite position and a definite momentum at the same time. If it is in a state of definite position, its momentum is completely uncertain. If it is in a state of definite momentum, its position is completely uncertain. But the uncertainty principle is not the same thing as wave function collapse. The uncertainty principle tells you that certain pairs of properties cannot both be definite. Wave function collapse tells you that measurement forces a system from an indefinite state into a definite one. These are related but distinct aspects of quantum mechanics. The uncertainty principle is about the limits of simultaneous knowledge. Wave function collapse is about the transition from potentiality to actuality. So what causes this transition? One possibility is that measurement requires interaction with a macroscopic apparatus. When a quantum system interacts with a large, classical measuring device, the superposition of the quantum system becomes entangled with the macroscopic states of the device. The device might have a pointer that indicates one value or another. The pointer cannot be in a superposition of pointing to different values because macroscopic objects decohere almost instantly. So the interaction with the device forces the quantum system into a definite state that corresponds to a definite state of the pointer. But this just pushes the problem back one step. Why does the device have a definite pointer position? It is made of particles, and particles obey quantum mechanics, so the device should also be in a superposition. And if you include the device in your quantum description, The superposition does not collapse, it just spreads. The system and the device together enter a superposition where each possible measurement outcome is correlated with a corresponding state of the device. The wave function does not collapse, it evolves unitarily, continuously, according to the Schrödinger equation. If you then include the observer looking at the device, the same thing happens. The observer becomes entangled with the system and the device. The observer enters a superposition of seeing different outcomes, and if you try to include the observer's environment, the laboratory, the air molecules, the photons bouncing around, everything becomes entangled in an ever-expanding superposition. Nothing collapses. The wave function just grows to encompass more and more systems. This is called the measurement chain problem, and it leads to an uncomfortable conclusion. If you take quantum mechanics seriously and apply it to everything, including measuring devices and observers, then wave function collapse never happens. The universe is always in a superposition of all possible outcomes of all possible measurements. What we experience as collapse is just our subjective perspective within one branch of the superposition. This is the essence of the many worlds interpretation. There is no collapse, there is only branching, and every possible outcome occurs in some branch. But most physicists do not accept this. The idea that every quantum event splits the universe into countless parallel realities seems extravagant and difficult to test. So they look for other explanations. Maybe collapse is a real physical process that happens when a quantum system interacts with a sufficiently large or complex system. Maybe there is a threshold, a certain number of particles, a certain level of entanglement, beyond which the superposition becomes unstable and collapses spontaneously. This would solve the measurement problem without requiring parallel universes. But no one has found a consistent way to formulate such a theory. Every attempt to add a collapse mechanism to quantum mechanics either predicts effects that have not been observed or introduces inconsistencies. Another approach is to deny that collapse happens at all, but in a different way than the many worlds interpretation. This is the approach of decoherence theory. Decoherence says that when a quantum system interacts with its environment, the different branches of the superposition become effectively independent. They no longer interfere with each other. From the perspective of an observer within one branch, it appears that the wave function has collapsed. But in reality, the full superposition still exists. It is just that the different branches are decoupled and cannot observe each other. Decoherence explains why we see definite outcomes even though the wave function has not collapsed. It explains why Schrödinger's cat is either alive or dead, not both. The cat is a macroscopic system constantly interacting with its environment. The superposition of alive and dead decoheres so rapidly that the two branches become independent. An observer inside the box sees a definite outcome, either an alive cat or a dead cat, not because the wave function has collapsed, but because the observer is entangled with one branch of the superposition and cannot access the other branch. But decoherence does not fully solve the measurement problem. It explains why superpositions appear to collapse from the perspective of an observer within the system. It does not explain why we experience one outcome rather than another. In the decoherence picture, both outcomes still exist in the full quantum state. The observer sees one or the other, but both are real. This brings us back to something like the many worlds interpretation. Decoherence and many worlds are closely related. Both deny that collapse is a real physical process. Both say that all outcomes occur. The main difference is whether you interpret the different branches as separate worlds or as different components of a single wave function. There is another, more radical possibility. Maybe collapse is related to consciousness. Maybe it's the act of a conscious observer becoming aware of a measurement outcome that causes the wave function to collapse. This was suggested by some of the founders of quantum mechanics, including Eugene Wigner and John von Neumann. The idea is that the measurement chain continues until it reaches a conscious mind, and it is at that point that the superposition collapses into a definite outcome. This interpretation is deeply controversial. Most physicists reject it because it gives consciousness a special role in the laws of physics, and there is no independent evidence that consciousness has such a role. It also raises more questions than it answers. What counts as consciousness? Does a mouse collapse wave functions? What about an insect? What about an artificial intelligence? And if consciousness causes collapse, how does it do so? What is the mechanism? No one has been able to formulate a consistent theory along these lines, and yet the question remains. If collapse is not caused by consciousness, and not caused by decoherence, and not a result of interaction with a macroscopic apparatus, then what causes it? The standard textbook answer is that collapse happens when a measurement occurs, and a measurement is an interaction with a classical measuring device. But this answer is circular. It defines measurement in terms of classical devices, but classical devices are made of quantum particles, so they should obey quantum mechanics too. The boundary between quantum and classical is not sharp, it is fuzzy, and this fuzziness is at the heart of the measurement problem. In practice, physicists work around this problem by treating macroscopic objects as classical, even though they are fundamentally quantum. This approximation works extremely well for making predictions. You can calculate the probability of different measurement outcomes, and those probabilities match experimental results with extraordinary precision. But the approximation does not explain what is happening. It does not tell you whether collapse is real or illusory, whether it is physical or psychological, whether it happens at a particular moment or gradually over time. What we are left with is a theory that works but that we do not fully understand. Quantum mechanics is the most successful scientific theory ever developed. It underlies all of modern technology: semiconductors, lasers, MRI machines, GPS satellites. It has been tested in countless experiments, and it has never been wrong. And yet, we do not agree on what it means. We do not know what happens during a measurement. We do not know whether particles have properties when unobserved. We do not know whether the wave function is a real physical thing or just a mathematical tool. This uncertainty is not temporary. It is not a gap that will be filled by more research. It is a fundamental ambiguity in our understanding of reality. The quantum world does not behave the way the classical world does, and the transition between them is not well defined. Measurement is the interface between the quantum and the classical, and we do not understand how that interface works. We can describe it mathematically, we can predict its outcomes, but we cannot explain it. And this means that at the most basic level, we do not know what reality is. We know how it behaves when we measure it, but we do not know what it is when we are not looking. You think of objects as separate things. The chair is distinct from the table. Your body is distinct from the air around you. A particle is a localized entity, a point or a small region in space that has properties like mass and charge. This separateness feels fundamental. Objects have boundaries. They begin and end. They are here and not there. But quantum field theory tells us that this picture is wrong. There are no particles, not in the sense of discrete, localized objects. There are only fields. And fields are not made of anything. They are the fundamental substance of reality. A field is a mathematical object that assigns a value to every point in space and time. It exists everywhere, filling all of space. And what we call particles are excitations of these fields. Ripples, disturbances, localized vibrations in the underlying structure. The electromagnetic field is the simplest example. You are familiar with this field even if you do not think of it that way. When you place a magnet near a piece of iron, the iron moves. The magnet exerts a force on the iron across empty space. There is nothing visible connecting them, but the force is real. The explanation is that the magnet creates a magnetic field, a region of space where magnetic forces can be felt. The iron responds to this field. The field is not just a mathematical convenience. It is a physical thing. It carries energy. It can propagate as waves. Light is a wave in the electromagnetic field. Radio waves, microwaves, X-rays, all of these are oscillations of the electromagnetic field traveling through space. In classical physics, the field is continuous. It can have any value at any point. But in quantum field theory, the field is quantized. Its energy comes in discrete units called quanta. For the electromagnetic field, the quantum is the photon. A photon is not a particle in the traditional sense. It is a packet of energy in the electromagnetic field. When the field oscillates with a certain frequency and amplitude, we say there is a photon present. When the field is in its lowest energy state, we say there are no photons. But the field itself is always there. It exists even when no photons are present. The vacuum is not empty. It is filled with fields in their ground state, and this is true for every type of particle. Electrons are excitations of the electron field. Quarks are excitations of quark fields. Neutrinos are excitations of neutrino fields. There is a field for every fundamental particle, and these fields exist everywhere in the universe. They overlap, they interact, they permeate all of space. When you see an electron, you are seeing a localized disturbance in the electron field. When the electron moves, the disturbance moves. When the electron disappears, when it annihilates with a positron, the disturbance in the electron field goes away, and disturbances in other fields appear, usually photons. Energy is transferred from one field to another, but nothing is created or destroyed in the sense of objects coming into or going out of existence. The fields are always there. Only their excitation states change. This changes what it means for something to exist. An electron is not a thing that exists independently. It is a pattern of energy in a field, and that field extends throughout all of space. The electron is not confined to a point or even to a small region. It is a localized excitation, but the field itself is non-local. This means that in a deep sense, the electron is connected to everything else. It is part of a universal structure. The separateness you perceive, the distinctness of the electron from other particles, is an approximation that works at low energies and large distances. But at the fundamental level, everything is part of the same interconnected web of fields. When two particles interact, they are not colliding like billiard balls. They are not even exchanging forces in the way you might imagine. They are interacting through their fields. An electron and a photon interact because the electron field couples to the electromagnetic field. The coupling is described by a term in the equations that allows energy to be transferred from one field to another. When we say an electron emits a photon, what we mean is that energy in the electron field decreases and energy in the electromagnetic field increases, and the pattern of this energy transfer looks like a particle moving away from another particle. But there are no particles, there are only fields and their interactions. This picture becomes even stranger when you consider virtual particles. In quantum field theory, the vacuum is not a state of nothingness. It is a state where fields are fluctuating constantly. These fluctuations are called quantum fluctuations, and they are not just mathematical artifacts. They have measurable effects. The Casimir effect, for example, is caused by vacuum fluctuations of the electromagnetic field. If you place two uncharged metal plates very close together in a vacuum, they experience a small attractive force. This force arises because the vacuum fluctuations between the plates are restricted. Only certain wavelengths fit between the plates, while the fluctuations outside are unrestricted. The difference in vacuum energy creates a pressure that pushes the plates together. Virtual particles are another consequence of these fluctuations. A virtual particle is a temporary excitation of a field that appears and disappears within a time interval allowed by the uncertainty principle. These particles do not have enough energy to persist indefinitely. They borrow energy from the vacuum, exist briefly, and then disappear, returning the energy. Virtual particles are involved in every interaction between real particles. When an electron repels another electron, it does so by exchanging virtual photons. These photons are not directly observable. They exist only as intermediaries in the interaction, but they are necessary to make the mathematics work. The force between charged particles is mediated by the exchange of virtual photons. This means that the vacuum is not empty. It is seething with activity. Particle-antiparticle pairs are constantly appearing and annihilating. Fields are fluctuating at every point in space. The energy of these fluctuations is called vacuum energy, or zero-point energy. In principle, if you add up the vacuum energy of all fields at all points in space, you get an infinite result. This is one of the unresolved problems in theoretical physics. The predicted vacuum energy is infinite, but the observed vacuum energy, measured through the cosmological constant, is extremely small, but not zero. The discrepancy is enormous, and no one knows how to resolve it. But the key point is that fields are not emergent properties. They are not approximations or useful fictions. They are the fundamental entities. Everything else, particles, forces, matter, energy, is derived from fields and their interactions. You're not made of particles. You're made of excitations in quantum fields. Your body is a complex, highly organized pattern of field excitations, held together by interactions between those fields. The atoms in your body are not discrete objects. They are stable configurations of electron fields and quark fields, bound together by the electromagnetic and strong nuclear forces, which are themselves mediated by other fields. And these fields do not stop at your skin. The electron field that makes up part of your body extends throughout the universe. It is the same field that makes up electrons in distant stars. There is only one electron field, and all electrons are excitations of that single field. This does not mean that all electrons are the same electron, but it does mean that they are not independent entities. They are different excitations of the same underlying structure. The separateness you perceive is a high-level description. At the fundamental level, there is no separation. There is only the field. This has philosophical implications. If everything is a pattern in fields, and fields are continuous and non-local, then the universe is not made of separate objects. It is a unified whole. The distinctions we draw between you and the chair, between the Earth and the Sun, between one particle and another, are conventional. They are useful for describing the world at macroscopic scales, but they do not correspond to fundamental divisions in reality. The universe is one interconnected system, and what we call objects are just regions where the field configurations are particularly stable or intense. This view is sometimes called field ontology. It says that fields are what exist and everything else is derivative. But even this is not the final picture, because quantum field theory is not the most fundamental theory we have. It works extremely well for describing particles and forces at energies we can access with current technology, but it breaks down at very high energies and very small distances. At the Planck scale, distances around 10 to the minus 35 meters and energies around 10 to the 19 giga-electron volts, quantum field theory predicts infinities and inconsistencies. This suggests that it is an approximation to a deeper theory, one that we have not yet fully formulated. String theory is one candidate for this deeper theory. In string theory, fields are not fundamental. What we call particles are not excitations of fields, but different vibrational modes of tiny one-dimensional strings. The electron is one mode of vibration, the photon is another, and so on. The fields of quantum field theory emerge as low-energy approximations to the dynamics of these strings. But string theory is still incomplete, and it makes predictions that are difficult or impossible to test with current technology. So while it provides a possible framework for going beyond quantum field theory, it is not yet a confirmed description of reality. Loop quantum gravity is another approach. It says that space-time itself is quantized, made of discrete loops and networks at the Planck scale. Fields are excitations of this quantized geometry. Again, this is speculative, and the theory is not yet complete. But the point is that even the field picture, as fundamental as it seems, may be only an approximation. There may be something deeper still. Reality may be made of structures we have not yet imagined. But whatever the ultimate theory turns out to be, the lesson from quantum field theory is clear. The world is not made of separate localized objects. It is made of continuous overlapping structures that extend throughout space. What you perceive as distinct and separate is a coarse-grained approximation. At the deepest level we currently understand, everything is connected. Not metaphorically, but literally. The fields that make up your body are the same fields that make up everything else. You are not a separate entity in the universe. You are a pattern in the universe, a temporary localized excitation in a sea of fields that fills all of space and time. You experience time and space as universal structures. Right now is right now, everywhere. When something happens here, it happens at the same moment that other things are happening elsewhere. You might not know what is happening on the other side of the planet, but you assume that there is a fact of the matter about what is occurring there right now. The present moment is global. It extends across all of space. This assumption feels inevitable. Time flows at the same rate for everyone. A second is a second, no matter where you are or how fast you're moving. But this assumption is wrong. Special relativity, formulated by Einstein in 1905, showed that there is no universal present. Simultaneity, the concept of events happening at the same time, is relative. It depends on your state of motion. Two observers moving at different velocities will disagree about whether two distant events occur simultaneously, and both observers are correct. There is no objective fact about which events are happening now across the universe. The present moment is not a global property. It is local to your reference frame. This is not an illusion caused by the finite speed of light. It is not that you see distant events with a delay because light takes time to reach you. That delay exists, but relativity goes deeper. Even after you correct for light travel time, observers in different reference frames will still disagree about the order of events. What one observer sees as simultaneous, another sees as separated in time. What one observer sees as happening in one order, another may see as happening in the reverse order, and both observations are equally valid. The reason for this is that the speed of light is constant in all reference frames. This is the foundational postulate of special relativity. No matter how fast you're moving, you will always measure light travelling at the same speed, approximately 300 million meters per second in vacuum. This sounds strange, because in everyday life speeds add. If you are on a train moving at 50 kilometers per hour, and you throw a ball forward at 20 kilometers per hour relative to the train, the ball is moving at 70 kilometers per hour relative to the ground. But light does not work this way. If you are on a spaceship moving at half the speed of light and you shine a flashlight forward, the light does not travel at 1.5 times the speed of light. It travels at the speed of light, exactly the same as it would if you were stationary. This constancy of the speed of the light has profound consequences. It means that time and space cannot be absolute. They must adjust to ensure that light always travels at the same speed in all reference frames. If you're moving relative to me, your clock runs slower from my perspective, and distances along your direction of motion are contracted. These are not optical illusions. They are real physical effects. Time genuinely passes more slowly for you, and distances are genuinely shorter. And from your perspective, my clock is the one running slowly, and my distances are contracted. Both perspectives are correct. There is no privileged reference frame, no absolute standard of rest. This symmetry leads to the relativity of simultaneity. Imagine two events occurring at different locations in space. Event A happens on Earth. Event B happens on Mars. If you are stationary relative to Earth and Mars, and the events are arranged so that light from both reaches you at the same time, you will conclude that the events were simultaneous. But if you are moving toward Mars and away from Earth, light from event B will reach you before light from event A, even after you correct for your motion. You will conclude that event B happened first, and if you are moving toward Earth and away from Mars, you will conclude that event A happened first. All three conclusions are correct within their respective reference frames. This means that the concept of now is not universal. Your now, the set of all events that are simultaneous with your current moment, is different from my now if we are moving relative to each other. And this is not just a matter of perspective or perception. It is a fundamental feature of space-time. The universe does not have a universal present moment. It has a structure in which different observers slice space-time into space and time in different ways, and each slicing is equally valid. Einstein realized that space and time are not separate entities. They are aspects of a single four-dimensional structure called space-time. Events do not occur at a particular location in space and a particular moment in time. They occur at a particular point in space-time. And the way you separate space-time into space and time depends on your motion. If you are stationary, you divide space-time one way. If you are moving, you divide it differently. But the space-time itself is the same. It is only your perspective on it that changes. This is similar to how different observers might describe the same object in space, using different coordinate systems. One person might say an object is to the north. Another, facing a different direction, might say it is to the left. Both are correct. They are simply using different orientations. In relativity, time and space are like directions in space-time. What one observer calls a distance in space, another might call partly distance in space and partly distance in time. The space-time interval between two events is invariant. All observers agree on it. But the separation into spatial distance and temporal duration is relative. This relativity of simultaneity leads to paradoxes if you think about it in classical terms. The twin paradox is one of the most famous. Imagine two twins. One stays on Earth, the other travels to a distant star at nearly the speed of light and then returns. When the travelling twin comes back, less time has passed for her than for the twin who stayed on Earth. She has aged less. This is not because of acceleration or deceleration. It is because time passes more slowly in a moving reference frame. The travelling twin's clock and her biological processes run slower from the perspective of the earthbound twin. But this raises a puzzle. From the travelling twin's perspective, she is at rest, and the Earth is moving away and then toward her. So shouldn't the earthbound twin age less? The resolution is that the situation is not symmetric. The travelling twin changes reference frames when she turns around to come back. She experiences acceleration. The earthbound twin does not. This breaks the symmetry and makes it unambiguous that the travelling twin ages less. But the underlying point remains: time is not universal. It depends on motion and acceleration. General relativity extends this principle to include gravity. Gravity is not a force in the traditional sense. It is a curvature of space-time caused by mass and energy. Massive objects like the Earth or the Sun warp the space-time around them, and other objects move along the straightest possible paths in this curved space-time. What we experience as gravitational attraction is actually the geometry of space-time guiding our motion. You are not being pulled toward the Earth. You're following the natural curvature of space-time created by the Earth's mass, and this curvature affects time as well as space. Time passes more slowly in stronger gravitational fields. If you are standing on the surface of the Earth, your clock runs slightly slower than a clock in orbit. This effect is tiny for everyday purposes, but it is real and measurable. GPS satellites must correct for it. If they did not account for the time dilation caused by their weaker gravitational field and their orbital velocity, their position calculations would accumulate errors of several kilometers per day. Near a black hole, where space-time curvature is extreme, time dilation becomes dramatic. If you were to hover near the event horizon of a black hole and then return to a distant observer, you would find that much more time had passed for the distant observer than for you. From your perspective, you were near the black hole for a few hours. From the distant observer's perspective, decades or centuries might have passed. This is not science fiction. It is a prediction of general relativity, confirmed by numerous observations and experiments. What this means is that there is no universal clock. There is no objective rate at which time passes. Time is relative to your position in a gravitational field and to your state of motion. Different observers experience different durations between the same two events, and all of these experiences are correct. There is no privileged observer who experiences the true rate of time. Time is relative, and the relativity is not an artifact of measurement. It is a fundamental feature of the universe. The implications for the concept of now are even more troubling. If simultaneity is relative, then the question of what exists right now has no objective answer. If you are on Earth and you ask what is happening on a planet orbiting a star 10 light-years away, the answer depends on your motion. If you are at rest relative to that planet, there is a specific set of events occurring there now. But if you're moving toward or away from the planet, a different set of events is occurring there now. The two sets can be separated by years. Events that are in the future for one observer can be in the present or even the past for another observer moving differently. This does not violate causality. You cannot use this relativity to send information into the past or to affect events before they occur. The light cones, the set of events that can causally influence or be influenced by a given event, are absolute. All observers agree on what is in the future light cone and what is in the past light cone of an event. But events outside the light cone, events that are space-like separated, have no objective temporal order. They are neither unambiguously in the past nor in the future. Their temporal relationship is ambiguous, dependent on the observer's reference frame. This is deeply disorienting. It means that the present moment as you conceive it does not extend across the universe. There is no cosmic now. There is only your now, and it is different from everyone else's now. The universe does not have a global state at a given time. It has a four-dimensional structure, and different observers carve that structure into space and time in different ways. What you call the present is a three-dimensional slice through four-dimensional space-time, and the angle of that slice depends on your velocity and position in a gravitational field. If the present is not universal, then the flow of time is not universal either. The sensation you have of time passing, of moments coming into existence and then receding into the past, is not a feature of the universe. It is a feature of your consciousness. The universe does not flow through time. It exists as a four-dimensional block, and you move through it, or more accurately, you are a four-dimensional structure extended through time, and your consciousness experiences different slices of that structure sequentially. But the sequence is not built into the universe. It is built into you. This is what relativity reveals. Time and space are not the rigid universal structures you assumed. They are flexible, relative, observer-dependent. The world does not have a single objective present moment. It does not have a universal frame of reference. Every observer has their own perspective, their own division of space-time into space and time, and all perspectives are equally valid. Reality is not a three-dimensional space evolving through time. It is a four-dimensional space-time, and your experience of it is a narrow, subjective slice through that larger structure. You think of reality as made of matter and energy. Particles have mass. Fields carry energy. Objects are physical things, tangible and substantial. This seems like the most fundamental description. The universe is made of stuff, and that stuff interacts according to physical laws. Information is something that describes the stuff. It is secondary, derived, a property of configurations rather than a constituent of reality itself. But there is a growing perspective in physics that reverses this hierarchy. Information may not be a property of physical systems. Physical systems may be a property of information. The universe may be fundamentally informational, and what we call matter and energy may be the way that information manifests when viewed at certain scales and under certain conditions. This is not mysticism. It is an idea emerging from thermodynamics, quantum mechanics, and the study of black holes. The first hint that information might be fundamental comes from the second law of thermodynamics. Entropy, as you have seen, is a measure of disorder. But it has another interpretation. Entropy is also a measure of missing information. When you know the exact microstate of a system, the position and velocity of every particle, the entropy is zero. You have complete information. But if you only know the macrostate, properties like temperature and pressure, then many different microstates are consistent with what you know. The entropy is the logarithm of the number of possible microstates. It quantifies your ignorance. This means that entropy is not just a physical quantity, it is an informational quantity. And the second law of thermodynamics, which says that entropy always increases, can be understood as saying that information is always being lost. When you break an egg, you lose information about the exact arrangement of molecules. When heat spreads out, you lose information about where the energy was concentrated. The universe is moving from states of high information, low entropy, to states of low information, high entropy. And this process is irreversible. The connection between information and thermodynamics was made explicit by Claude Shannon in the 1940s. Shannon developed a mathematical theory of information to analyze communication systems. He defined information in terms of uncertainty. A message carries information if it reduces your uncertainty about something. The amount of information is measured in bits, the number of binary questions you need to answer to remove the uncertainty, and Shannon showed that the formula for information is mathematically identical to the formula for entropy in thermodynamics. The two concepts are the same, just applied in different contexts. This raises a question. If entropy is information, and entropy is a fundamental property of physical systems, then is information itself fundamental? Is the universe made of information, with matter and energy being secondary manifestations? This question became urgent in the study of black holes. A black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape from inside a boundary called the event horizon. Black holes form when massive stars collapse, compressing matter into an infinitely dense point called a singularity. The event horizon is not a physical surface. It is a boundary in space-time beyond which all paths lead inward. Once something crosses the event horizon, it cannot return. It will inevitably fall toward the singularity. In the 1970s, Stephen Hawking and Jacob Bekenstein discovered something surprising. Black holes have entropy, and the entropy of a black hole is proportional not to its volume, as you might expect, but to the area of its event horizon. This is strange. For normal objects, entropy depends on the number of particles, which scales with volume, but for black holes, the entropy depends on surface area. This suggests that the information about everything inside the black hole is somehow encoded on the surface of the event horizon. This is called the holographic principle. It says that the information content of a volume of space can be encoded on its boundary. The three-dimensional interior is, in some sense, a projection or hologram of the information stored on the two-dimensional surface. This has profound implications. It suggests that space itself might be emergent, that the three-dimensional universe you experience is a holographic projection of information stored on a distant two-dimensional boundary. The holographic principle is not just a curiosity. It appears in string theory, in the study of quantum gravity, and in attempts to reconcile quantum mechanics with general relativity. It suggests that the fundamental description of the universe is not in terms of matter and fields, existing in three-dimensional space, but in terms of information encoded on a lower dimensional boundary. Space and matter emerge from this information in the way that a three-dimensional image emerges from a two-dimensional hologram. If this is correct, then what you perceive as physical objects moving through space are actually informational structures. Your body is not made of particles in the traditional sense. It is a pattern of information, and the particles, fields, and forces that seem to constitute you are the way this information appears when projected into three dimensions. The separateness you perceive is a feature of the projection, not of the underlying information. At the fundamental level, everything is connected because everything is part of the same informational structure. But how can information be physical? In everyday language, information is abstract. It is something you read in a book or store on a computer. It does not seem like the kind of thing that could be the substance of reality. But in physics, information is not abstract. It is tied to physical states. A bit of information corresponds to a system that can be in one of two distinguishable states. The state of the system is the information, and changing the state requires energy. Information has a physical cost. This is formalized in Landauer's principle, which says that erasing a bit of information in a computational process generates a minimum amount of heat. Information is not just recorded by physical systems, it is instantiated in them. It is inseparable from the physical substrate. This leads to the idea that the universe might be computational. If reality is fundamentally informational, and information is processed according to rules, then the universe might be executing a computation. The laws of physics are the algorithm. The state of the universe at one moment determines the state at the next moment, just as the state of a computer at one time step determines the state at the next. This does not mean the universe is a computer, in the sense of a machine built by humans. It means that the mathematical structure of the universe resembles computation. Physical processes are information processing. This perspective has gained traction in quantum information theory. Quantum states can store and process information in ways that classical states cannot. Entanglement, superposition, and interference are informational resources. Quantum computers exploit these resources to perform certain calculations more efficiently than classical computers, and the behavior of quantum systems can be understood in terms of information flow and transformation. The wave function is not just a description of a physical state. It is a repository of information, and the evolution of the wave function is information processing. Some physicists go further and suggest that the universe is literally a computer simulation. This is the simulation hypothesis. It says that our reality is not the base level of existence, but a computed reality running on some more fundamental substrate. The idea is that if it is possible to create realistic simulations of universes, and if such simulations are created many times, then statistically, we are more likely to be living in a simulation than in the original base reality. This argument is controversial and speculative, but it takes seriously the idea that reality could be fundamentally computational. But even without invoking simulations, the informational perspective changes how we think about what exists. If matter and energy are manifestations of information, then what is information made of? The answer is that information is not made of anything. It is the fundamental ontology. It is what exists, and everything else is derived from it. This is similar to how fields are fundamental in quantum field theory. Fields are not made of anything more basic. They are the substrate. In the informational picture, information plays the same role. It is the bedrock of reality. This raises the question of what information is information about. In communication theory, information is about something. A message carries information about the state of a sender or about an event. But in fundamental physics, information does not seem to be about anything external. It is intrinsic. The information in a quantum state is not a description of something else. It is the state itself. The distinction between the map and the territory collapses. The information is the territory. This is conceptually difficult. We're used to thinking of information as representational, as referring to something beyond itself. But in the informational view of physics, information is self-contained. It does not represent physical reality. It is physical reality. The bits and qubits, the patterns and correlations, the flow and transformation of information. These are not descriptions of underlying processes. They are the processes. There is nothing beneath them. If this picture is correct, then the question of what reality is has a surprising answer. Reality is information. The universe is a structure of relationships, patterns, and correlations. What we call matter is a particular kind of informational structure. What we call energy is the capacity to change informational states. What we call space and time are the framework in which information is organized and processed. And consciousness, the subjective experience of being, might be another informational phenomenon, an emergent property of certain complex informational structures processing information about themselves. This does not make reality less real. It does not mean the universe is an illusion or that nothing matters. It means that the substrate of reality is different from what common sense suggests. You're not a collection of particles. You're a pattern of information instantiated in physical processes. And that pattern is just as real, just as substantial, as any other conception of what it means to exist. The information is not separate from the physics. It is the physics, and you are part of it, a localized, self-organizing, self-aware configuration of information embedded in a larger informational structure that we call the universe. You assume that the reality you experience is the only layer of reality. The universe exists and you exist within it, and there is nothing beyond or outside of it. This seems like the simplest, most parsimonious assumption. Adding extra layers, realities within realities, simulations within simulations, feels unnecessary and unfalsifiable. Why complicate the picture when the straightforward explanation works perfectly well? But there is an argument that challenges this assumption, and it does so not through metaphysics but through probability. If it becomes technologically possible to create realistic simulations of conscious beings, and if civilizations that reach this capability tend to create many such simulations, then the number of simulated realities would vastly outnumber base reality. Most conscious observers would be living in simulations, not in the original universe. And if most observers are simulated, then statistically you are probably simulated too. This is the core of the simulation hypothesis, and it is not as easy to dismiss as it might initially seem. The argument was formalized by philosopher Nick Bostrom in 2003. He proposed that at least one of three statements must be true. First, civilizations like ours almost never reach the technological capability to create realistic simulations of conscious beings. Second, civilizations that reach this capability choose not to create such simulations, perhaps for ethical reasons or lack of interest. Third, we are almost certainly living in a simulation. If the first two are false, if advanced civilizations both can and do create ancestor simulations, then simulated realities outnumber base reality by an enormous factor, and the probability that you are in base reality becomes vanishingly small. This is not proof that we are in a simulation. It is a conditional probability argument. It says that if certain assumptions hold, the simulation hypothesis is more likely than the alternative. And those assumptions are not implausible. Humanity is already creating increasingly sophisticated simulations. Video games, virtual reality environments, and AI-generated worlds are primitive versions of what might become possible in the future. If computational power continues to increase, and if consciousness can be simulated, a significant if, then creating realistic simulated universes might be achievable within centuries or millennia. And if one civilization creates such simulations, it might create millions or billions of them. The computational cost of running additional simulations once the technology exists could be trivial compared to the resources available to an advanced civilization. Each simulation could contain billions of conscious beings living entire lifetimes, unaware that their reality is computed. The number of simulated beings would quickly exceed the number of non-simulated beings. And this creates the statistical argument. If you are a randomly selected conscious observer, and most conscious observers are simulated, then you are probably simulated. But how could you tell? If the simulation is sufficiently detailed, it would be indistinguishable from base reality from the inside. The simulated beings would experience physical laws, sensory inputs, and causal structures that are entirely consistent. They would develop science, discover the laws governing their simulated universe, and never encounter any evidence that their reality is computed. The simulation would be closed, self-consistent, and complete within its own frame of reference. There could be hints, though, glitches or artifacts that reveal the underlying computational structure. If the simulation has finite resolution, if space and time are discretized at some fundamental scale, then extremely precise measurements might detect that discretization. The Planck length and Planck time, the smallest scales at which our current physics makes sense, could be hints of an underlying computational grid, but they could also be fundamental limits of base reality. There is no way to distinguish between the two from within the system. Another possibility is that the simulators intentionally leave evidence. They might embed signatures in the laws of physics, patterns in the cosmic microwave background, or anomalies in particle interactions that could only be explained as deliberate design. But this assumes the simulators want to be discovered, and there is no reason to assume that. If the purpose of the simulation is to study how civilizations develop naturally, revealing the simulation would contaminate the experiment. The simulators would have an incentive to remain hidden. A more disturbing possibility is that the simulation is not perfect, but the imperfections are subtle and rare. Occasionally, the laws of physics might fail in small localized ways. An object might spontaneously disappear or appear. A measurement might yield an impossible result. Memories might be inconsistent, but these glitches would be so infrequent and isolated that they would be dismissed as hallucinations, measurement errors, or anomalies. The simulation does not need to be perfect. It only needs to be good enough that the inhabitants cannot conclusively prove it is a simulation. The simulation hypothesis also raises questions about the purpose of the simulation. Why would anyone create it? One possibility is ancestor simulation. Advanced civilizations might simulate their own history to understand their origins, to test counterfactual scenarios, or simply out of curiosity. In this case, the simulated beings are not arbitrary constructs but models of actual historical populations. You might be a simulated version of a person who once existed in base reality, recreated in a simulation to see how history would have unfolded under slightly different conditions. Another possibility is entertainment. The simulation could be a game, a narrative, or an art project. The beings inside it are characters in a story, and their experiences are designed to be interesting or meaningful to an external audience. This is less comforting than ancestor simulation, because it implies that suffering and death within the simulation are intentional features, included to create drama or emotional impact. The simulators would be aware of every painful moment you experience, and they would have chosen to include it. A third possibility is research. The simulation could be a scientific experiment designed to study the emergence of complexity, consciousness, intelligence, or civilization. The parameters of the simulation, the physical constants, the initial conditions, might be varied across many runs to see what kinds of universes produce life, or what kinds of life produce technology, or what kinds of technology lead to existential risks. In this scenario, you are a data point. Your choices and experiences contribute to whatever question the simulators are trying to answer, or the simulation might have no purpose at all, at least not from your perspective. It might be a byproduct of some other process. Simulations might be created automatically as part of a larger computational system, with no intentional design or oversight. The universe you inhabit could be an accident, a spontaneous emergent structure within a vast computational substrate that serves some entirely unrelated function. The simulators might not even be aware that your simulation exists. The simulation hypothesis also complicates questions of identity and existence. If you are simulated, are you less real? The immediate reaction is to say yes. Simulated beings are not real in the way that base-level beings are real. They are copies, imitations, shadows of true existence. But this distinction is harder to maintain upon reflection. What does it mean to be real? If your experiences are indistinguishable from those of a non-simulated being, if your consciousness has the same structure and content, if your thoughts and feelings are equally vivid and meaningful, then in what sense are you less real? Philosophers have debated this question for centuries, long before computers existed. Descartes considered the possibility that an evil demon was deceiving him about the nature of reality, feeding him false sensory experiences. He concluded that even if he was being deceived, the fact that he was thinking proved that he existed. The thinking itself was undeniable. The same logic applies to simulated beings. If you are simulated, you still exist. You are still conscious. Your experiences are still real to you. The substrate of your existence is different, but existence itself is not diminished. In fact, base reality might also be substrate dependent in ways we do not understand. If the informational view of physics is correct, then even non-simulated beings are patterns of information instantiated in physical processes. The difference between a simulated being and a base-level being is only a matter of which computational substrate is running the information processing. Both are informational structures. Both are physically realized. The distinction between simulated and real collapses if reality itself is computational. This leads to a more unsettling thought. If we are in a simulation, what is the nature of the reality running the simulation? Is it also a simulation? If advanced civilizations in base reality create simulations, and those simulations become advanced enough to create their own simulations, then you could have a hierarchy of nested simulations. Each level believes it is close to base reality, but in fact there could be many layers above it. The base reality, if it exists, could be vastly different from anything any simulated civilization could imagine. Its physical laws, its ontology, its structure could be entirely alien. And there is no way to determine how many layers deep you are. You could be in the first level of simulation, created directly by base reality. Or you could be in the 1000th level, a simulation within a simulation within a simulation, each layer progressively more removed from the original substrate. The laws of physics you observe are the laws programmed into your level of simulation, but they might bear no resemblance to the laws of base reality. Everything you think you know about the universe, quantum mechanics, relativity, thermodynamics, might be artifacts of the simulation, simplified rules designed to approximate something far more complex or entirely different. This is deeply disorienting. It means that even the most fundamental discoveries of science might not be ultimate truths. They are truths about your simulated universe, but not about reality itself. And if you cannot access base reality, you can never know whether your discoveries correspond to anything beyond the simulation. Science becomes the study of the rules of the simulation, not the study of fundamental reality. It is still useful, still predictive, still meaningful within your frame of reference, but it is not ultimate. The simulation hypothesis also raises ethical questions. If you suspect you're in a simulation, how should you behave? Do your actions matter? If the simulation can be paused, rewound, or deleted at any moment, does that diminish the significance of your choices, or does it make them more significant because they are all you have? If the simulators are watching, should you try to communicate with them to plead for mercy or demand answers? Or should you ignore the possibility entirely and live as if base reality and simulated reality are indistinguishable? Most physicists do not take the simulation hypothesis seriously as a scientific question because it is not falsifiable. Any evidence you might find for a simulation could also be explained as a feature of base reality. Any absence of evidence could be explained as the simulation being well designed. The hypothesis is consistent with all possible observations, which means it does not constrain your expectations about what you will observe. It is metaphysically interesting but empirically empty, and yet it remains unsettling, because the argument is probabilistic, not metaphysical. If simulations are possible, and if they are created in large numbers, then you are statistically more likely to be in one than not. The hypothesis does not require exotic assumptions or violations of known physics. It only requires that consciousness can be simulated, and that advanced civilizations choose to create such simulations. Both of these seem plausible, though neither is certain, and if they are true, then the straightforward assumption that you are in base reality becomes the less probable option. Quantum mechanics, as you have seen, describes systems in terms of wave functions that exist in superpositions of multiple states. The wave function evolves deterministically according to the Schrödinger equation until a measurement occurs, at which point it collapses into a definite state. But what counts as a measurement? What physical process causes the collapse? And does it require something special, something like consciousness, to make the transition from quantum superposition to classical definiteness? These questions lead to the observer problem, one of the most perplexing and unresolved issues in the foundations of quantum mechanics. The problem arises because the theory seems to require a division between the quantum system being measured and the classical observer doing the measuring. But if everything is made of quantum particles including the observer, then where does this division occur? What makes an observer different from any other physical system? In the early days of quantum mechanics, some physicists suggested that consciousness plays a special role. The idea was that the wave function remains in superposition until a conscious observer becomes aware of the measurement result, and it is this act of conscious observation that causes the collapse. This was not a fringe view. John von Neumann, one of the greatest mathematicians of the 20th century, included consciousness in his formulation of quantum measurement. Eugene Wigner, a Nobel Prize-winning physicist, also argued that consciousness must be involved, because otherwise the measurement chain never terminates. The measuring device is quantum, so it goes into superposition with the system. The laboratory is quantum, so it goes into superposition with the device. The chain continues indefinitely unless something non-quantum, something outside the system, intervenes, and consciousness seemed like the only candidate. Wigner illustrated this with a thought experiment known as Wigner's friend. Imagine a friend inside a laboratory performing a quantum measurement. The friend observes a definite result. The particle is spin up, for example. But from Wigner's perspective outside the laboratory, the entire lab, including his friend, is a quantum system. Until Wigner opens the door and asks his friend what happened, the lab is in a superposition of the friend having observed spin up and the friend having observed spin down. The friend experiences a definite result, but Wigner's description of the system includes both possibilities in superposition. Whose description is correct? Does the collapse happen when the friend observes the result, or when Wigner learns about it? This paradox reveals a tension in quantum mechanics between subjective experience and objective description. The friend experiences a single outcome. There is no ambiguity from the friend's perspective. The measurement happened, the result is definite, and the wave function has collapsed. But from Wigner's perspective, using the rules of quantum mechanics to describe the entire laboratory, the wave function has not collapsed. It has simply become entangled with the friend's state. Both perspectives seem valid, but they contradict each other. The most straightforward resolution is to deny that consciousness has any special role. Decoherence explains why macroscopic systems like friends and laboratories appear to be in definite states, even though they are technically in superpositions. When a quantum system interacts with a large, complex environment, the different branches of the superposition become effectively independent. They no longer interfere with each other. From within one branch, it looks as though the wave function has collapsed, even though the full quantum state includes all branches. This removes the need for a conscious observer. The environment acts as an observer, continuously decohering quantum systems into apparent definiteness. But decoherence does not fully solve the observer problem. It explains why superpositions are not observed macroscopically, but it does not explain why any particular outcome is experienced. If the wave function includes all possible measurement results in superposition and decoherence simply makes them non-interfering, then all results still exist in the quantum state. The question of why you experience one result rather than another remains unanswered. Decoherence tells you that the different outcomes are separated into different branches. It does not tell you why your consciousness is associated with one branch and not the others. The many worlds interpretation embraces this ambiguity. It says that all outcomes occur and your consciousness splits along with the branching of the wave function. There is a version of you that observed spin up and a version that observes spin down, and both are equally real. Consciousness does not collapse the wave function. It simply follows one branch, and there are other versions of you following the other branches. In this view, the observer is not special. Observation is just entanglement. You become correlated with the system you are measuring, and the correlation creates the illusion of a single outcome because each version of you can only experience their own branch. But this raises a different problem. If all outcomes occur, why do you experience probabilities? Why does the Born rule, the rule that says the probability of an outcome is proportional to the square of the amplitude of the corresponding component of the wave function, accurately predict how often you observe different results? In the many worlds interpretation, every outcome happens with certainty in some branch. So where do probabilities come from? Why do high amplitude branches feel more likely than low amplitude branches? There is no consensus answer. Some proponents of many worlds argue that probability is a subjective notion, related to rational betting behavior or self-locating uncertainty. Before you perform a measurement, you do not know which branch you will find yourself in, so you assign probabilities based on the amplitudes of the branches. But this explanation feels circular. It defines probability in terms of your expectations, but your expectations are supposed to be derived from the probabilities given by quantum mechanics. The attempt to explain why the Born rule holds in a deterministic branching universe remains one of the unsolved challenges of the interpretation. Other interpretations take consciousness more seriously. The von Neumann-Wigner interpretation explicitly includes consciousness as a fundamental part of the theory. The physical world evolves according to the Schrödinger equation, but consciousness is not physical in the same way. It is something else, something that can interact with the quantum state and cause collapse. This dualism, the idea that there are two kinds of substance, physical and mental, is philosophically problematic. It requires explaining how consciousness interacts with physical systems, what the laws governing this interaction are, and why consciousness is necessary for collapse when unconscious measurement devices seem to work just fine. An alternative is the participatory universe idea, suggested by physicist John Archibald Wheeler. In this view, observers do not merely record pre-existing facts about the universe, they participate in bringing those facts into existence. The universe is not fully determined until it is observed. The past is not fixed until a measurement in the present retroactively selects which past occurred. This sounds bizarre, but it is consistent with certain quantum experiments, such as delayed choice experiments, where a decision made after a particle has passed through an apparatus affects the outcome in a way that seems to reach backward in time. Wheeler's interpretation says that observation is not passive. It is an active role in the unfolding of reality. The observer and the observed are not separate. They are co-creators of what becomes real. But even without invoking consciousness explicitly, the observer problem reveals something unsettling. Quantum mechanics requires a split between the system and the observer. The system evolves according to quantum rules. The observer, or at least the recording of the measurement result, is treated classically. But where is the boundary? If you include the measuring device in the quantum system, it becomes entangled with the particle. If you include the scientist reading the device, the scientist becomes entangled. If you include the laboratory, the photons bouncing around, the air molecules, the Earth, the solar system, everything becomes entangled. The boundary between quantum and classical is not sharp. It is arbitrary. You can place it wherever you want for practical purposes, but there is no fundamental line in nature separating the quantum from the classical. This arbitrariness suggests that the observer is not a physical thing, but a conceptual role. An observer is whatever you treat as being outside the quantum system for the purposes of analysis. It is a choice you make when setting up the problem, not a feature of reality. But this makes the notion of observation subjective. Different choices of where to place the boundary give different descriptions of the same situation, and yet, the predictions all agree. Quantum mechanics is extraordinarily successful at predicting experimental results, regardless of where you draw the line between system and observer. What this means is that quantum mechanics works as a predictive tool without requiring a clear ontology. You do not need to know what counts as an observer, or whether collapse is real, or whether consciousness plays a role. You only need to follow the rules, evolve the wave function, calculate probabilities using the Born rule, compare predictions to measurements. The theory works, but it does not tell you what is happening. It does not tell you what an observer is, or why measurement is different from any other interaction, or what reality is like when no one is looking. And yet, the observer problem cannot be entirely dismissed as philosophical. It affects how we interpret experiments. It affects what questions we think are meaningful to ask. It affects whether we believe that reality has a definite state independent of observation. These are not just abstract concerns. They shape the direction of research, the design of experiments, the interpretation of results. Physicists who believe in objective collapse develop different theories than physicists who believe in many worlds or pilot waves or Copenhagen pragmatism, and none of these theories have been ruled out by experiment. The observer problem is a reminder that science does not give you reality directly. It gives you models, predictions, frameworks for organizing observations, and those frameworks are extraordinarily successful, but they do not always tell you what is real. They tell you what you will observe under certain conditions, and the gap between observation and reality, between what we can measure and what exists independently of measurement, remains open. The observer is at the center of this gap. Observation is the interface between the quantum and the classical, between the potential and the actual, between the mathematical formalism and lived experience. And we do not understand how that interface works. You are made of atoms. Atoms are made of protons, neutrons, and electrons. Protons and neutrons are made of quarks. Quarks and electrons are excitations of quantum fields governed by the laws of physics. These laws are precise, deterministic at the level of the wave function, and they describe how fields interact, how particles move, how forces propagate. The behavior of a single electron is described by quantum mechanics. The behavior of two electrons interacting is also described by quantum mechanics. In principle, the behavior of 10 to the 27th electrons, along with all the other particles in your body, is also described by quantum mechanics. But you do not behave like a quantum field. You think. You make decisions. You experience emotions. You have intentions, beliefs, desires, and a sense of self. None of these properties are present in the fundamental laws. There is no equation in quantum field theory that predicts consciousness or purpose or meaning, and yet these things exist. They are real aspects of your experience. They emerge from the interactions of particles that individually have none of these properties. This is emergence, and it is one of the deepest and least understood phenomena in nature. Emergence occurs when a system composed of simple parts, following simple rules, exhibits behavior that cannot be easily predicted or understood by looking at the parts individually. The behavior is a property of the system as a whole, not of the components. It arises from the interactions, the organization, the patterns that form when many parts come together in specific ways, and once it arises, it operates according to its own principles, which can be studied and understood without reference to the underlying parts. Temperature is a simple example. A single atom does not have a temperature. Temperature is a property of a large collection of atoms, a measure of their average kinetic energy. You cannot predict the temperature of a gas by examining one molecule. You need to consider billions of molecules moving and colliding in chaotic, random ways. From this chaos, a stable, measurable property emerges, and once it emerges, it behaves according to the laws of thermodynamics, which do not reference individual atoms. You can study heat flow, phase transitions, and thermal equilibrium without ever thinking about molecules. The macroscopic behavior is autonomous from the microscopic details. Life is a more complex example. A living cell is made of molecules, proteins, lipids, nucleic acids, each one obeying the laws of chemistry. But a cell is not just a collection of molecules. It is a self-organizing, self-replicating system. It maintains its own structure, repairs damage, responds to its environment, reproduces. These are properties of the system, not of the individual molecules. No single protein is alive. No strand of DNA is alive. Life emerges from the interactions of these components, from the way they are organized into networks and cycles and feedback loops. And once life emerges, it can be studied on its own terms. Biology is not reducible to chemistry, even though living systems are made of chemicals. There are principles of biology, natural selection, homeostasis, metabolism, that operate at a higher level of organization. Consciousness is the most mysterious example. Your subjective experience, the redness of red, the feeling of pain, the sense of being someone, arises from the activity of neurons in your brain. Neurons are cells. Cells are made of molecules. Molecules are made of atoms. Atoms are quantum fields. And yet, nowhere in the description of quantum fields is there anything resembling subjective experience. The hard problem of consciousness, as philosopher David Chalmers calls it, is explaining why and how physical processes give rise to subjective experience. Why does it feel like something to be you? Why is there an inner life, a qualitative dimension to existence, when the underlying physics is purely quantitative? There is no agreed-upon answer. Some philosophers and scientists believe consciousness is strongly emergent, meaning it is a fundamentally new kind of property that arises at a certain level of complexity, but cannot be reduced to the underlying physics. Others believe it is weakly emergent, meaning it is in principle explainable in terms of neural activity, but the explanation is so complex that we need higher-level concepts to make sense of it. Still, others believe consciousness might require new physics, something beyond the current understanding of quantum mechanics and neuroscience. But regardless of the explanation, consciousness exists. You experience it directly. And it is not present in the individual neurons or synapses or molecules. It is a property of the system. It emerges from patterns of activity. From the way information is integrated and processed across billions of neurons, the patterns are what matter, not the substrate. In principle, if you could replicate the same patterns in a different substrate, silicon instead of carbon, electrical circuits instead of neurons, the same conscious experience might arise. This is the functionalist view of consciousness, and it suggests that what you are is not the matter you're made of, but the patterns that matter instantiates. This has implications for identity and continuity. You replace most of the atoms in your body over the course of a few years. The cells in your skin, your liver, your blood, they die and are replaced. Even neurons, which were once thought to be permanent, can be replaced in some regions of the brain, and yet you remain you. Your sense of identity persists even though the physical substrate is changing. What persists is not the matter, but the pattern, the organization, the information. You're a process, not a thing, a dynamic structure that maintains itself over time by constantly rebuilding its components. This is true at every level of organization. A wave in the ocean is not made of the same water molecules from moment to moment. The water moves in circular patterns and the wave moves forward, but the wave is a pattern propagating through the medium, not a movement of the medium itself. A hurricane is not a physical object in the traditional sense. It is a self-organizing pattern of airflow and pressure gradients. The air molecules that make up the hurricane at one moment are different from the molecules that make it up a minute later. But the hurricane persists because the pattern persists. You are similar. Your body is not a static collection of atoms. It is a pattern of processes, chemical reactions, energy flows, information exchanges that maintain a stable configuration over time. The configuration is what defines you, not the specific particles, and this pattern is hierarchical. At the lowest level there are quantum fields and particles, at the next level there are atoms and molecules, above that cells and tissues, above that organs and systems, and at the highest level there is you, a conscious, thinking, feeling entity with goals and intentions and a sense of self. Each level has its own properties and its own principles, and these properties are not reducible to the levels below. They emerge from the organization and interactions of the lower level components. This hierarchical structure is what allows complexity to exist. If everything had to be understood in terms of quantum fields, the universe would be incomprehensible. There are too many particles, too many interactions, too much information to track. But emergence allows us to ignore the lower levels when studying higher levels. You do not need to know the quantum state of every atom in your body to understand how your muscles work. You can study muscles at the level of cells and proteins and chemical signals, and that level has its own coherent description. The lower levels are still there, still operating, but they are not relevant to the questions you're asking. This is why science is divided into disciplines. Physics studies the fundamental laws, chemistry studies molecules and reactions, biology studies life, psychology studies behavior and cognition, sociology studies groups and cultures. Each level has its own concepts, its own methods, its own explanations. And while everything ultimately reduces to physics in the sense that all higher level phenomena are made of physical stuff, the explanations at higher levels are autonomous. They do not require constant reference to the levels below. Emergence creates new levels of reality with their own logic and structure. But emergence is not magic. It does not violate the laws of physics. The higher level properties are consistent with the lower level laws, even if they are not easily derivable from them. A hurricane obeys the laws of fluid dynamics, which are derived from the laws governing air molecules. Consciousness, whatever its ultimate explanation, must be consistent with the laws of neuroscience and biology and chemistry and physics. The higher levels are constrained by the lower levels, even though they are not reducible to them. This raises the question of whether reality has a fundamental level. Is there a bottom, a lowest level of description beyond which there is nothing more basic? Or is it levels all the way down, with each level emerging from a deeper level indefinitely? Current physics suggests there is a fundamental level, at least in terms of particles and fields. Quarks, electrons, photons, and the other particles of the Standard Model are described as fundamental. They are not made of anything smaller, but even this might be provisional. String theory suggests that particles are not fundamental, but are vibrational modes of strings, and strings themselves might emerge from something more basic. The question remains open. And there is a corresponding question about the top. Is there a highest level of organization, a most complex emergent structure? Or can complexity increase indefinitely, with new levels of organization emerging as systems become larger and more intricate? Human civilization is an emergent structure. It arises from the interactions of billions of individuals, each one pursuing their own goals, and yet patterns emerge. Economies, governments, cultures, technologies that operate according to their own principles. These patterns are real. They shape your life in profound ways, and they are not reducible to individual psychology, even though they are made of individuals. Perhaps the universe itself is an emergent structure. Perhaps the laws of physics, the constants of nature, the fundamental fields, perhaps these emerge from something deeper, something we have not yet conceived. The informational view of physics suggests this might be the case. If reality is fundamentally informational, then the physical laws are emergent properties of the way information is organized and processed. The particles and fields are not the bottom level. They are higher level descriptions of underlying informational dynamics. This perspective inverts the usual picture. Instead of starting with particles and building up to complexity, you start with information or computation or some even more abstract structure, and particles emerge as patterns within that structure. Space and time might also be emergent, not fundamental. They might arise from the relationships and interactions of more basic entities, whatever those entities are. This is speculative, but it is taken seriously in some approaches to quantum gravity. What all of this reveals is that reality is layered. It is not a single, monolithic thing, but a hierarchy of structures, each one emerging from the level below and giving rise to the level above. You exist at one of these levels. You are an emergent property of biological processes, which are emergent properties of chemical processes, which are emergent properties of physical processes, and you, in turn, participate in higher level structures, social systems, cultural patterns, technological networks that have their own emergent properties. You're both a whole and a part, a unity and a multiplicity, an individual and a node in a larger system. And this is not a paradox, it is the nature of emergence. Reality builds itself from the bottom up, and each level is real in its own right. There is a limit to how precisely you can measure the universe. This is not a practical limitation, not a matter of better instruments or more advanced technology. It is a fundamental boundary built into the structure of reality itself. At the smallest scales and highest energies, the concepts that organize your understanding of the world, space, time, causality, even measurement itself, begin to break down. Physics reaches a point where its own equations stop making sense, where predictions become infinite or undefined, where the distinction between something existing and something not existing becomes unclear. This boundary is set by the Planck scale, named after Max Planck, who discovered the quantum of action in 1900. The Planck length is approximately 10 to the negative 35 meters. The Planck time is approximately 10 to the negative 44 seconds. The Planck energy is approximately 10 to the 19 giga-electron volts. These are not arbitrary units. They are combinations of fundamental constants, the speed of light, the gravitational constant and Planck's constant, that define the scales at which quantum mechanics and general relativity both become important and can no longer be treated separately. At distances larger than the Planck length, you can usually ignore quantum effects when thinking about gravity, or ignore gravity when thinking about quantum effects. But at the Planck length, both matter equally. Space-time becomes quantum, and our current theories, quantum field theory and general relativity, are not equipped to handle this. General relativity describes space-time as a smooth, continuous geometry that can be curved by matter and energy. Quantum mechanics describes fields and particles as discrete, probabilistic, and subject to uncertainty. These descriptions are incompatible at the Planck scale. They predict different things, and we do not yet have a theory that unifies them. This is not just a theoretical problem, it has real consequences for what can be measured. If you try to measure a distance smaller than the Planck length, the energy required to probe that scale is so high that it would create a black hole. The black hole's event horizon would be larger than the distance you're trying to measure, making the measurement impossible. The universe, in a sense, resists being examined beyond a certain resolution. The act of probing smaller scales disrupts space-time so severely that the measurement destroys its own conditions. This suggests that space-time might not be continuous. It might be discrete at the Planck scale, made of tiny indivisible units like pixels on a screen. In this view, space is not infinitely divisible. There is a smallest possible length, a fundamental granularity to the fabric of reality. Time would also be discrete. ticking forward in Planck time intervals rather than flowing smoothly. This discreteness would explain why measurement below the Planck scale is impossible. There is nothing below it. The Planck scale is the resolution of reality itself. But this raises deep questions. If space-time is discrete, what are the discrete units? Are they points, loops, networks? String theory and loop quantum gravity offer different answers. In string theory, the fundamental objects are one-dimensional strings vibrating in higher dimensional spaces, and space-time emerges from the collective behavior of these strings. In loop quantum gravity, space-time is made of quantized loops and nodes forming a network called a spin network, and geometry emerges from the connectivity and properties of this network. Both approaches suggest that space-time is not fundamental, but emergent, built from something more basic. And if space-time is emergent, then the Planck scale is the scale at which the emergence begins to be visible. Below it, the smooth geometry we experience breaks down into discrete quantum structures. Above it, those structures coalesce into the continuous space-time described by general relativity. The Planck scale is the boundary between the quantum and the geometric, the point where the universe transitions from one description to another. This has implications for what you can know. Information is physical, and physical systems are constrained by quantum mechanics and relativity. The Heisenberg uncertainty principle limits how precisely you can know both the position and momentum of a particle. The speed of light limits how quickly information can travel, and the Planck scale limits how much information can be encoded in a given region of space. There is a maximum density of information set by the point at which the region would collapse into a black hole. This limit is called the Bekenstein bound, and it says that the maximum entropy, the maximum number of distinguishable states of a region of space, is proportional to the area of its boundary, not its volume. This is another hint of the holographic principle, the idea that three-dimensional space might be a projection of information encoded on a two-dimensional surface. The Bekenstein bound implies that you cannot measure or store arbitrarily large amounts of information in a finite region. There is a limit to how finely you can distinguish between different states. This means that the universe is, in some sense, finite in its informational content, even if it is infinite in spatial extent. Any finite region has a finite number of possible states, and this finiteness places limits on what can be computed, what can be observed, what can be known. This also means that there are questions you cannot answer, not because of practical limitations, but because the questions are not well defined below the Planck scale. What is the exact position of a particle at the Planck length? The question assumes that position can be defined with arbitrary precision, but it cannot. What happened at the first Planck time after the Big Bang? The question assumes that time can be subdivided indefinitely, but it might not be able to. What is the geometry of space-time inside a black hole singularity? The question assumes that geometry is well defined at infinite curvature, but it is not. These are not questions waiting for better theories to answer. They might be questions that have no answers because they refer to structures that do not exist. This is uncomfortable. Science is built on the idea that questions have answers, that the universe is knowable, that with enough effort and ingenuity you can understand anything. But the Planck scale suggests otherwise. It suggests that there is a boundary to knowledge, not because of ignorance or lack of resources, but because reality itself has a limit. Below the Planck scale, the concepts you use to describe the world, space, time, measurement, causality, may not apply. And if they do not apply, then the questions you formulate using those concepts are meaningless. This does not mean that nothing exists below the Planck scale. It means that whatever exists there is not describable in the language of space and time. It might be describable in some other language, some other set of concepts that we have not yet developed. String theory and loop quantum gravity are attempts to develop such a language, but they are incomplete and speculative. The correct description might be something entirely different, something that has not yet been imagined. And even above the Planck scale there are limits. Quantum mechanics introduces fundamental indeterminacy. You cannot predict the exact outcome of a quantum measurement, only probabilities. You cannot know both position and momentum with arbitrary precision. These are not limitations of your knowledge, they are limitations of reality itself. The universe does not have a definite state for these quantities. They're genuinely indeterminate until measured, and measurement selects one possibility from many but does so randomly, without a deeper cause. This randomness is not ignorance, It is intrinsic to the structure of quantum mechanics. General relativity also introduces limits. The speed of light limits how quickly information can propagate. Events beyond your light cone cannot affect you, and you cannot affect them. This creates a horizon, a boundary beyond which you cannot see. If the universe is expanding and the expansion is accelerating, then there are galaxies that are moving away from you faster than light. Not through space. Nothing moves through space faster than light, but because space itself is expanding. These galaxies are beyond your cosmological horizon. Their light will never reach you. They are forever inaccessible, and you can know nothing about them. The observable universe is only a small part of the total universe, and the part you cannot observe is, by definition, unknowable. This means that cosmology is limited. You can study the universe within your horizon, but you cannot study the universe as a whole unless the whole is finite and contained within your horizon. If the universe is infinite, or if it extends beyond your horizon, then there are questions about the total universe that you can never answer. How big is the universe? What is its global geometry? What is happening in regions beyond your horizon? These questions have no empirical answers. You can speculate. You can extrapolate from the part you can see, but you cannot observe or test your speculations. This is a profound limitation. It means that some aspects of reality are inaccessible, not temporarily but permanently. The universe has regions you can never visit, events you can never observe, information you can never obtain, and this inaccessibility is not a failure of technology or imagination. It is built into the structure of space-time. The universe hides parts of itself from every observer, and no observer has access to the whole. Even within the observable universe, there are limits to what you can measure. Quantum fluctuations in the vacuum create noise at small scales. The cosmic microwave background, the relic radiation from the Big Bang, sets a limit on how precisely you can observe distant galaxies, because photons from the background interfere with photons from the galaxies. Dark matter and dark energy, which make up most of the universe's mass and energy, are invisible. They do not emit light. They can only be detected through their gravitational effects, and even those effects are subtle and difficult to measure precisely. These limits are not temporary. They are not gaps that will be filled by future discoveries. They are boundaries imposed by the laws of physics themselves. The universe is not infinitely knowable. It is partially knowable, and the parts you cannot know are not defects or mysteries to be solved. They are features of the structure of reality. The universe does not owe you complete knowledge. It does not provide access to all of its information. It reveals some things and hides others, and this hiddenness is as fundamental as the things it reveals. This is a humbling realization. It means that science, for all its power and success, is limited. It can answer many questions, but not all questions. Some questions are beyond the reach of measurement, beyond the reach of theory, beyond the reach of knowability. And this is not a failure of science. It is a recognition of the nature of reality. The universe is larger, stranger, and more complex than any description we can give. It exceeds our concepts, our mathematics, our ability to measure and predict. And this excess is not accidental, it is structural. Reality is more than we can know, and it always will be. You make a choice, you decide to turn left instead of right. The moment passes, the decision is made. The other possibility, the version of events where you turned right, vanishes. It does not happen. It is not real. This is how you experience choice and causation. One thing happens, and all the other things that could have happened do not. The present moment selects a single future from many possibilities, and those other futures cease to exist. But according to one interpretation of quantum mechanics, this is not what happens. Every possible outcome of every quantum event actually occurs. The universe does not select one possibility and discard the others. It realizes all of them simultaneously in different branches of reality. When you measure a particle's spin and find it is up, there is another branch of reality where you measured it and found it is down. Both outcomes happen. Both versions of you exist. You simply cannot communicate across branches, so each version of you experiences only one outcome and believes that the other did not occur. This is the many worlds interpretation, first proposed by Hugh Everett in 1957. It is one of the most radical ideas in physics, and also one of the most mathematically straightforward. It takes the Schrödinger equation seriously and applies it to everything, including observers. It says that the wave function never collapses. It evolves continuously, deterministically, and all the possibilities encoded in the wave function are real. What we experience as collapse is simply the branching of the wave function into multiple non-interacting components, each one corresponding to a different outcome. The universe is constantly splitting into parallel realities, and every quantum event creates new branches. This resolves the measurement problem by eliminating it. There is no collapse. There is no special role for measurement or observation. The observer is just another quantum system, and when the observer becomes entangled with the system being measured, the combined system enters a superposition. Each branch of the superposition is a separate reality, and within each branch, the observer sees a definite outcome. The appearance of collapse is an artifact of being inside one branch. You cannot see the other branches, but they exist. They are as real as the branch you are in. The implications are staggering. Every time a quantum measurement occurs, the universe splits, and quantum measurements occur constantly, at every scale, in every interaction between particles. Electrons collide, photons are absorbed, atoms decay. Each of these events is a quantum process with multiple possible outcomes, and each one creates new branches. The number of branches is incomprehensibly vast. Every moment, the universe is dividing into an unimaginable multitude of parallel realities, each one slightly different from the others. In one branch, you are reading the sentence. In another, you stopped reading a moment ago. In another, you never started. In another, you do not exist because your parents never met. In another, you exist, but the Earth was struck by an asteroid in the Cretaceous period, and humans never evolved. In another, the laws of physics are slightly different and atoms cannot form. The branching extends to every possible configuration of matter and energy consistent with the laws of quantum mechanics. All of these branches are real. All of them are happening, and you are present in countless branches, living slightly different versions of your life. Most of the branches are nearly identical to yours. The differences are microscopic. A single atom decays in one branch and not in another. A photon is absorbed at a slightly different time. An electron's spin is measured and found to be up instead of down. These differences do not affect macroscopic events, so the branches remain almost indistinguishable. Your experience in one branch is the same as your experience in the other, but over time, small differences accumulate. A photon absorbed at a different moment might trigger a different neural firing in your brain, leading to a different thought, a different decision, a different action. The branches diverge, and once they diverge, they remain separate. There is no mechanism for branches to merge. The splitting is irreversible. This means that there is no single you. There are countless versions of you, each one existing in a different branch, each one experiencing a different sequence of events. Some versions are almost identical, differing only in microscopic details. Others are radically different, having made different choices, experienced different events, lived different lives. And all of them are equally real. There is no preferred branch, no original version, no main timeline. Every branch is just as valid as every other branch. This raises the question of personal identity. If there are countless versions of you, which one is really you? The answer is that they all are. You are not a single entity. You're a structure that exists across many branches, or more accurately, you are a structure within a single branch, and there are other structures in other branches that are also you, in the sense that they share your past up to the point of branching. Before the branching, you were one entity. After the branching, you are many. But each version of you has continuity of experience. Each one remembers the same past up to the point of divergence. Each one feels like the same person. But you do not experience the branching. You do not feel yourself splitting into multiple versions. From your subjective perspective, only one outcome occurs. You measure the particle, and it is either spin up or spin down, not both. The many worlds interpretation explains this by saying that you do split, but the different versions of you cannot communicate. Each version exists in a separate branch, and the branches are decohered. They no longer interfere with each other. So each version of you has a single definite experience, and each one believes that the other outcomes did not happen. The subjective experience of collapse is real, but the objective collapse is not. The wave function contains all branches, but you only perceive one. This raises the question of probability again. If all outcomes occur, why do some outcomes seem more likely than others? The Born rule, which gives the probability of each outcome, is built into the standard formulation of quantum mechanics. But in many worlds there is no collapse, so there is no moment when one outcome is selected over others with certain probabilities. All outcomes occur with certainty. So where does probability come from? Proponents of many worlds argue that probability is subjective. It is a measure of your uncertainty about which branch you will find yourself in. Before you perform a measurement, you do not know which version of you will be the one you experience. If there are 10 branches with high amplitude and one branch with low amplitude, you are more likely to find yourself in one of the high amplitude branches simply because there are more of them, weighted by amplitude. Probability, in this view, is a statement about self-locating uncertainty. It is not about which outcome will happen, they all happen, but about which outcome you will experience. But this explanation is controversial. It feels circular. You use probability to predict which branch you will experience, but the reason high amplitude branches are more probable is that you define probability in terms of amplitude. Critics argue that many worlds does not derive the Born rule, it assumes it, and without a derivation, the interpretation is incomplete. Supporters counter that the same is true of other interpretations. They also postulate the Born rule without deriving it from deeper principles. The debate remains unresolved. Another objection to many worlds is that it is ontologically extravagant. It requires accepting the existence of an unimaginably vast number of parallel realities, most of which you can never observe or interact with. This seems to violate Occam's razor, the principle that simpler explanations are preferable. But supporters of many worlds respond that the interpretation is actually simpler in another sense. It has fewer postulates. It does not require a separate collapse mechanism. It does not require defining what counts as a measurement. It simply says that the Schrödinger equation is always valid, for all systems, at all times. The wave function evolves smoothly and deterministically. Nothing else is needed. The multiplicity of branches is not an added assumption. It is a consequence of taking the wave function literally. So is many worlds true? No experiment can distinguish it from other interpretations because all interpretations make the same predictions for observable outcomes. The differences are in what they say about the unobservable, what happens when you're not looking, what the wave function represents, whether other branches exist. These are metaphysical questions, not empirical ones. You can choose to believe in many worlds or not based on which explanation feels more satisfying, more coherent, more philosophically acceptable. But you cannot prove it with an experiment. What many worlds does is force you to confront the implications of taking quantum mechanics seriously. If the wave function is real, and if it evolves according to the Schrödinger equation without exception, then many worlds is the logical consequence. Every other interpretation adds something extra: a collapse mechanism, hidden variables, a special role for measurement or consciousness. Many worlds is what you get if you refuse to add anything extra, if you just follow the mathematics wherever it leads. And where it leads is to a universe that is far larger, far stranger, and far more populated than you ever imagined. A universe where every possibility is realized, where every choice you did not make was made by another version of you, where every outcome that could have occurred did occur somewhere, in some branch of an endlessly proliferating tree of realities. This does not make your choices meaningless. In your branch, your decisions still matter. They still shape your future, your experiences, your life. But they do not shape the totality of reality. Reality is larger than your choices. It contains all choices, all outcomes, all possibilities, and you are just one path through this infinite garden of forking paths. One version among countless versions, one branch among countless branches, one small part of an incomprehensibly vast whole. You experience the world as three-dimensional. You move through space in three directions: forward and back, left and right, up and down. Objects have volume, rooms have interiors. The universe extends outward in all directions, a vast three-dimensional expanse filled with galaxies and stars and planets. This dimensionality feels fundamental. Space is three-dimensional because that is what space is. It is a container, a stage, a framework in which things exist and events occur. But there is evidence suggesting that this three-dimensional experience is not fundamental. The information content of a region of space is not proportional to its volume, as you would expect in a truly three-dimensional reality. It is proportional to the area of the region's boundary. This is the holographic principle, and it implies that the three-dimensional universe you perceive might be a projection, an emergent structure derived from information encoded on a two-dimensional surface. The principle emerged from the study of black holes. When matter falls into a black hole, it crosses the event horizon and disappears from view. It seems to be lost, along with all the information it carried. But in the 1970s, Jacob Bekenstein and Stephen Hawking discovered that black holes have entropy. Entropy measures the number of possible microstates of a system, which is another way of saying it measures information. The surprising thing is that the entropy of a black hole is proportional to the area of its event horizon, not to the volume enclosed by the horizon. This is strange. For normal objects, entropy depends on volume. A box of gas has entropy proportional to the number of molecules, which scales with the volume of the box. But a black hole's entropy scales with the surface area of its event horizon. This suggests that all the information about what fell into the black hole is somehow stored on the horizon itself, encoded on a two-dimensional surface. The three-dimensional interior is not needed to account for the information content. The surface is enough. This led physicists to wonder whether the same principle applies to regions of space that are not black holes. Perhaps any region of space, not just a black hole, has its information encoded on its boundary. Perhaps the three-dimensional volume is redundant, a kind of hologram projected from the two-dimensional surface. This is the holographic principle, and it has found support in string theory, particularly in a result called the ADS/CFT correspondence. The ADS/CFT correspondence is a duality, a mathematical equivalence between two different theories. One theory describes gravity in a space called anti-de Sitter space, which has three spatial dimensions plus time. The other theory is a quantum field theory without gravity, defined on the boundary of that space, which has only two spatial dimensions plus time. The two theories are completely equivalent. Anything that happens in the three-dimensional interior can be described by a corresponding process on the two-dimensional boundary. The three-dimensional space with gravity is a hologram of the two-dimensional space without gravity. This is not just an analogy, it is a precise mathematical equivalence. You can calculate things in one theory and translate the results into the other theory, and they match. The interior and the boundary are two descriptions of the same reality, and because the boundary has one fewer dimension, the holographic principle is satisfied. The information in the three-dimensional volume is encoded on the two-dimensional boundary. If this duality applies to our universe, and there is no proof that it does but it might, then the three-dimensional space you experience is not fundamental. It is an emergent phenomenon, a projection from a two-dimensional description. The universe is, in some deep sense, a hologram, and you are part of that hologram. You are a pattern of information encoded on a distant surface, and your experience of moving through three-dimensional space is the way that information appears from the inside. This raises profound questions. Where is the boundary? If the universe is a hologram, what is the surface on which the information is encoded? For black holes, the surface is the event horizon. For the universe, the surface might be the cosmological horizon, the boundary of the observable universe, beyond which light has not had time to reach us. The information describing everything within the observable universe might be encoded on a sphere at the edge of that universe, and as the universe expands, the sphere expands, and more information can be encoded. The ADS/CFT correspondence applies to anti-de Sitter space, which has negative curvature and is not expanding. Our universe has positive curvature, or is flat, and is expanding. Whether a similar holographic duality applies to our universe is an open question. Some physicists believe it does. The mathematics is difficult and the physical interpretation is unclear. But even without a complete understanding, the holographic principle changes how we think about space. Space is not a pre-existing container into which objects are placed. It is an emergent structure that arises from the relationships and interactions of more fundamental entities. Those entities might be strings or quantum bits of information, or something else entirely. But whatever they are, they do not exist in three-dimensional space. They exist in some other framework, and three-dimensional space emerges from their collective behavior. This means that the volume you perceive, the sense that objects are inside space, that space has depth and interiority, is an illusion in a specific sense. It is not that space does not exist. It is that space is not what it seems. It is a higher level description, a convenient way of organizing information, but it is not the fundamental layer of reality. At the deepest level, there is no inside, no volume, no three-dimensionality. There is only the boundary, the surface, the two-dimensional encoding. And if space is emergent, then perhaps time is also emergent. Some approaches to quantum gravity suggest that time does not exist at the most fundamental level. There is no temporal evolution, no before and after. There is only a static, timeless structure, and time emerges as a feature of certain subsystems or certain perspectives within that structure. This is deeply counterintuitive, because time is so central to your experience. You perceive the flow of time, the passage from past to future, the irreversible arrow of becoming. But if time is emergent, then this flow is not fundamental. It is a derived property, an artifact of how information is organized and processed in the emergent three-dimensional space. The holographic principle also suggests that there is a maximum amount of information that can be stored in a given region. This is the Bekenstein bound, which says that the entropy of a region cannot exceed a certain value proportional to the area of the boundary. If you try to pack more information into a region than the bound allows, the region will collapse into a black hole. This means that the universe is finite in its informational content, at least locally. Any finite region has a finite number of distinguishable states, and this finiteness places limits on what can be computed, observed, or known within that region. This has implications for the nature of reality. If information is fundamental, and if there is a maximum density of information, then reality itself has a kind of granularity. It is not infinitely divisible. It is not continuous in the classical sense. It is discrete, pixelated, made of a finite number of bits or qubits or whatever the fundamental units of information turn out to be. And the three-dimensional space you experience is a coarse-grained, macroscopic approximation of this discrete structure. This picture is consistent with the idea that the universe might be computational. If reality is made of information, and if information is processed according to rules, then the universe is performing a computation. The laws of physics are the algorithm. The state of the universe, at one moment, determines the state at the next moment. And the computation is being performed on the two-dimensional boundary. Even though the results appear as a three-dimensional interior, you are part of the computation. Your thoughts, your experiences, your sense of self, all of these are informational processes occurring within the holographic structure. But this does not mean the universe is a simulation in the sense of being artificially created. The holographic principle does not imply a simulator or a creator. It simply says that the structure of reality is informational and that the three-dimensional space is not the fundamental layer. The universe might be a naturally occurring computational structure, self-contained and self-sufficient, with no external designer or programmer. The computation is not being run by something outside the universe. It is the universe. The universe is the computation. This is disorienting because it undermines the intuitive picture of space as a container. You think of yourself as existing at a location in space, with other objects at other locations, and space as the neutral background that holds everything. But if space is a hologram, then you do not exist at a location in space in the fundamental description. You are a pattern of information on a distant boundary, and your experience of being at a location is the way that pattern manifests in the emergent three-dimensional projection. And if this is true, then the separateness you perceive, the distance between you and other objects, the boundaries between things, is also an artifact of the projection. On the boundary, everything is connected. The information encoding you and the information encoding distant galaxies are part of the same structure, the same two-dimensional surface. The separation exists only in the three-dimensional space, which is emergent and not fundamental. At the deepest level, there is no separation. There is only the boundary, the encoding, the hologram, and you are part of it, inseparable from everything else. A localized pattern in a unified informational structure that appears from the inside as a vast three-dimensional universe. You have followed the explanations. You have seen how matter is mostly empty space, how vision captures only a narrow slice of the electromagnetic spectrum, how time is relative and not universal, how particles are excitations in fields, how measurement collapses wave functions in ways we do not fully understand, how reality might be informational or holographic or computational. You have confronted the possibility that you exist in a simulation, that consciousness might play a role in quantum mechanics, that there are many worlds branching at every moment, that space itself might be an emergent projection from a lower dimensional boundary. And yet, none of this changes what it feels like to be you. You still experience the world as solid, continuous, and three-dimensional. You still feel time flowing forward. You still sense yourself as a distinct entity, separate from your surroundings. The redness of red is still red. Pain still hurts. Joy still feels like joy. The abstractions of physics, no matter how accurate or fundamental, do not replace or diminish the immediate reality of your subjective experience. This is not a failure of understanding. It is a recognition that there are different kinds of truth. Physics describes the structure of reality, the patterns, the laws, the relationships between quantities. It tells you how things behave, how they interact, how they evolve over time. It provides models that make predictions, and those predictions are tested against measurements. When the predictions match the measurements, we say the model is successful. When they do not, we revise the model. This is the method of science, and it has been extraordinarily successful at uncovering the workings of the universe. But physics does not tell you what it feels like to experience those workings from the inside. It does not describe the qualitative texture of redness or the subjective sensation of pain. It does not capture what it is like to be a conscious observer embedded in the physical world. This is not because physics is incomplete, or because we have not yet discovered the right equations. It is because the language of physics is quantitative, relational, and objective. It describes third-person facts, things that can be measured and communicated and verified by anyone. But experience is first-person. It is private, immediate, and irreducible. And these two kinds of truth, objective and subjective, third-person and first-person, do not translate into each other. Philosophers call this the explanatory gap. You can describe all the physical processes occurring in a brain when someone sees the colour red, the wavelengths of light, the activation of cone cells in the retina, the neural signals travelling through the visual cortex, the patterns of firing across networks of neurons. You can map every step of the process in exquisite detail, and yet none of that explanation tells you what red looks like. None of it conveys the subjective quality of the experience. The description is complete from the outside, but it leaves out what it is like from the inside. This does not mean that consciousness is supernatural or that it violates the laws of physics. It means that the laws of physics, as currently formulated, describe behaviour and not experience. They tell you what systems do, not what systems feel, and there is no obvious way to bridge this gap. You cannot derive subjective experience from equations. You cannot deduce what pain feels like from a description of neural activity. The qualitative and the quantitative are different kinds of information, and the mapping between them, if it exists, is not understood. And yet, both are real. The physical world described by science is real. The atoms, the fields, the forces, they exist, and they operate according to laws that do not depend on whether anyone is observing them. But your experience is also real. The sensation of reading these words, the thoughts arising in your mind, the awareness of being someone. These are not illusions. They are not epiphenomena or byproducts. They are the most immediate and undeniable aspects of your existence. You know your own experience more directly than you know anything else. Everything you know about the external world comes through experience. And so, in a sense, experience is the foundation. It is what is given. Everything else is inferred. This creates tension. Science tells you that your experience is not a direct perception of reality. It is a constructed model generated by your brain based on limited sensory input. The solidity of objects is not actual solidity, but electromagnetic repulsion. The colours you see are not properties of light, but interpretations assigned by your visual system. The flow of time is not a universal feature of the universe, but an artifact of entropy and memory. Your sense of self is not a unitary, persistent entity, but an emergent pattern of neural activity, constantly changing, constantly reconstructed. And yet, knowing all of this does not change the experience. The table still feels solid when you touch it. Colours still look vibrant and distinct. Time still feels like it flows. You still feel like a continuous self, the same person you were yesterday, even though your atoms have changed and your memories have been altered. The experience persists, unchanged by the knowledge that it is constructed. This suggests that experience has a kind of autonomy. It operates at its own level, with its own logic, independent of the underlying mechanisms. You can study the brain and understand how it generates experience, but that understanding does not reduce experience to brain activity. Experience remains what it is, immediate, qualitative, first person. It is not eliminated by explanation. It is not dissolved by analysis. It is a layer of reality that coexists with the physical layer, and both are real. Some philosophers argue that experience is fundamental, that consciousness is not reducible to physical processes because it is a basic feature of the universe, like mass or charge. This view, called panpsychism, suggests that all matter has some form of experience, however rudimentary, and that human consciousness is a complex, integrated form of a more basic property. Others argue that experience is emergent, that it arises from information processing in sufficiently complex systems, and that there is no hard boundary between conscious and non-conscious systems, only a gradual increase in the richness and integration of experience. But regardless of which view is correct, the fact remains that experience is real, and it is not captured by the equations of physics. This does not make physics wrong or incomplete in the usual sense. Physics is extraordinarily successful at describing the behavior of matter and energy, but it is not designed to describe experience. It is designed to describe what can be measured, predicted, and communicated objectively. An experience by its nature is subjective. This means that there are truths about reality that are not accessible through science, not because science is limited by technology or funding or human ingenuity, but because science deals with a specific kind of truth, public, repeatable, quantifiable. Experience is private, unique, qualitative. It cannot be measured in the same way that mass or charge can be measured. You cannot weigh an experience or time it, or subject it to controlled experiments in the way you can with physical objects. You can correlate experience with physical processes. You can show that certain brain states are associated with certain experiences, but correlation is not identity. Knowing the brain state does not give you the experience. It only gives you information about the conditions under which the experience occurs. And so, you are left with two descriptions of reality, both valid, both irreducible. One is the description given by physics, a universe of fields and particles, forces and interactions, evolving according to mathematical laws. The other is the description given by experience, a world of colours and sounds, pleasures and pains, thoughts and feelings, all immediate and undeniable. These two descriptions do not contradict each other, but they do not merge into a single, unified account. They are complementary perspectives on the same reality, each one revealing something that the other cannot. This is not a problem to be solved. It is the structure of reality as we know it. Reality has both an objective aspect, accessible through measurement and mathematics, and a subjective aspect, accessible through direct experience. Both are real, both matter, and neither is more fundamental than the other. They are two sides of the same coin, two ways of encountering what is, and this duality extends to everything you have learned. Yes, matter is mostly empty space, but it still supports your weight. Yes, you only see a narrow band of the electromagnetic spectrum, but the colours you see are still vivid and meaningful. Yes, time is relative, but it still structures your life. Yes, particles are not particles in the classical sense, but the objects around you are still stable and reliable. Yes, the universe might be holographic or computational, or branching into many worlds, but your experience of it is singular, coherent, and continuous. The abstractions of physics do not negate the reality of experience. They complement it. They reveal the underlying patterns and structures, the laws and relationships that govern the behavior of matter and energy. But they do not replace the lived, felt reality of being a conscious observer in the world. Both are needed. Both are true. And together they give a richer, deeper picture of what reality is. You are not just a collection of particles, you're also an experiencer, a subject, a centre of awareness. And that awareness, that subjective interiority, is as much a part of reality as the particles themselves. It is not an illusion, It is not a trick of the brain. It is what it is like to be you. And that is real in the most fundamental sense, not because it can be measured or quantified, but because it is directly known. It is the ground of all knowledge, the precondition for all understanding, the starting point from which all inquiry begins. Science reveals that the universe is stranger than it appears. But it does not diminish the appearance. The strangeness and the appearance coexist. Two aspects of a single, unified reality that is large enough to contain both the equations and the experiences, both the measurements and the meanings, both the objective and the subjective. And you, standing at the intersection of these two domains, are both a physical system and a conscious being, both a part of the universe and a perspective within it.